Close your eyes for a moment and imagine this. Right now, this very second, somewhere 124 light years away from where you sit, there might be an ocean. Not just any ocean, but a planetary ocean so vast it could swallow all of Earth's seas twice over, stretching beneath a sky thick with hydrogen, where the horizon never ends because there is no land, only endless water meeting endless atmosphere. And in that ocean, if scientists are right, something might be alive. Something might be producing chemicals that, on our world, only life can make. Think about that. While you were born, grew up, learned to walk, went to school, fell in love, experienced heartbreak, that potential ocean world was there, orbiting its dim red star, possibly teeming with microscopic life we've never seen, never touched, never even imagined. How does that make you feel? Terrified? Excited? Impossibly small? Hold on to that feeling, because what I'm about to tell you will shake everything you thought you knew about our place in the universe. This isn't science fiction anymore. This is happening right now, in our time, in our generation. For thousands of years, humanity stared up at the night sky and wondered if we were alone. Philosophers debated it. Religious leaders pondered it. Science fiction writers dreamed about it. But we never had an answer. We never had proof. We were cosmic orphans, floating on a pale blue, convinced in our loneliness that the universe was dead and silent. Then something changed. Something magnificent and terrifying began to happen. In the span of just a few decades, we went from knowing almost nothing about the cosmos to discovering things so profound, so reality-shattering, that our ancestors would have thought us insane for even suggesting them. We found ripples in the fabric of space and time itself. We photographed black holes devouring matter. We detected planets made of diamond. We watched stars explode in real time. We discovered oceans hiding beneath the icy crusts of distant moons. And now, we might have found the signature of alien life. What you're about to hear isn't just a list of discoveries. This is the story of how everything we thought we knew was wrong. How the universe revealed itself to be stranger, more violent, more beautiful, and infinitely more complex than we ever imagined. These are the 30 most amazing space discoveries ever made, and they will change how you see reality itself. Let me start with something that will make your head spin. In September 2015, at precisely 5:51 in the morning, two enormous machines detected something impossible. Something Albert Einstein predicted a century ago but believed we would never be able to detect. The machines were called LIGO, the Laser Interferometer Gravitational Wave Observatory, and what they detected was a ripple in space-time itself. Not a ripple through space. A ripple in the actual fabric of space and time. Let that sink in for a moment. Space itself was vibrating, stretching and squeezing, because 1.3 billion years ago, two black holes, each dozens of times more massive than our Sun, collided with such violence that they sent shock waves through the entire universe. Think about what that means. The event happened when Earth was still a planet of simple, single-celled organisms. No animals, no plants, no complex life, just microbes floating in ancient seas. And for 1.3 billion years, this ripple traveled through space, moving at the speed of light, until it finally reached Earth on that September morning. The wave was so subtle that it stretched and compressed space by less than 1/10,000th the width of a proton. That's smaller than an atom. That's smaller than anything you can imagine. And we detected it. Do you understand what this means? We can now listen to the universe. Before LIGO, we could only see the cosmos through telescopes that detected light. But light can be blocked, scattered, absorbed. Gravitational waves pass through everything. They carry information about events so violent, so energetic, that they warp the very foundation of reality. And the discovery didn't stop there. Since that first detection, LIGO and its partner observatories have detected over 200 black hole collisions. 200 times, the universe has played its violent symphony, and we've been listening. We've heard neutron stars colliding, creating explosions that forge gold and platinum and all the heavy elements that make up your jewelry, your electronics, the very atoms in your body. We've confirmed Stephen Hawking's theorem that black holes must grow when they merge. We've detected intermediate mass black holes, mysterious objects that shouldn't exist according to our theories but do anyway, laughing at our assumptions. Here's something that should keep you awake at night. One of these collisions produced a black hole with a mass of 142 suns. 142 times the mass of the star that gives you life, compressed into a point of infinite density. The energy released in that merger was equivalent to 8 suns completely converting their mass into pure energy. That's more powerful than anything in the universe except the Big Bang itself. And it happened. Not in a computer simulation. Not in a theory. It actually happened out there in the real universe, and we detected the echo of its violence. Do you ever feel like the ground beneath your feet is stable? Like reality is solid and unchanging? It's not. Right now, as you listen to this, gravitational waves are passing through your body. Your atoms are being stretched and squeezed by collisions happening millions or billions of light years away. You're being touched by the violence of the cosmos, and you can't even feel it. The universe is far more dynamic, far more active than we ever suspected. But let's talk about something even stranger. Something that challenged not just our understanding of space, but our understanding of life itself. In April 2025, a team of scientists announced they had detected what they called the strongest evidence yet for biological activity beyond our solar system. The planet is called K2-18b, and it's unlike anything in our cosmic neighborhood. It's 8.6 times more massive than Earth, 2.6 times larger, and it orbits a dim red dwarf star in what scientists call the habitable zone. That's the region around a star where liquid water can exist. And that's where things get interesting. Using the James Webb Space Telescope, the most powerful telescope ever built by humanity, scientists pointed their instruments at K2-18b and analyzed the light filtering through its atmosphere as it passed in front of its star. What they found shocked them. The atmosphere contains methane and carbon dioxide, which is interesting but not revolutionary. What is revolutionary are two other chemicals they detected: dimethyl sulfide and dimethyl disulfide. On Earth, these chemicals are only produced by life. Only by microscopic marine organisms called phytoplankton. Only by biology. There is no known geological or chemical process that produces them in significant quantities without life. And on K2-18b, these chemicals are thousands of times more concentrated than on Earth. Think about what this implies. If this detection is real, if it holds up under scrutiny, then K2-18b might be what scientists call a Hycean world, a planet with a hydrogen-rich atmosphere hovering over a global ocean that could be up to 100 miles deep, containing twice as much water as all of Earth's oceans combined. And in that ocean, life might have emerged. Not intelligent life. Not aliens with technology and civilizations, but microscopic organisms, perhaps similar to the bacteria that dominated Earth billions of years ago, producing chemicals as they metabolize, as they reproduce, as they struggle to survive in their alien ocean. Now, here's the part where we have to be careful, where we have to temper our excitement with scientific caution. The detection is only at the 3 sigma level of statistical significance. That means there's a 0.3% chance it could be a random fluctuation, a cosmic coincidence. Scientists want 5 sigma, which means less than a 0.00006% chance of error. They need more observations, more data, more confirmation. And some scientists are skeptical. They point out that laboratory experiments have shown these chemicals can be produced without life under certain conditions. They question whether K2-18b might be too hot for life, with an atmosphere of magma and molten rock rather than water. They remind us that previous claims of biosignatures, like phosphine on Venus, turned out to be controversial and potentially explained by non-biological processes. But here's what's undeniable. For the first time in human history, we have the technology to detect potential signs of life on planets orbiting other stars. For the first time, we can analyze the atmospheres of worlds dozens or hundreds of light years away and search for the chemical fingerprints of biology. Whether K2-18b harbors life or not, the fact that we're even having this conversation, that we're even asking these questions with real data from a real planet, is extraordinary. Our children or grandchildren might live in a world where the existence of extraterrestrial life is not speculation but confirmed scientific fact. How will that change humanity? How will it change our religions, our philosophies, our understanding of what it means to be alive? These are questions we'll need to answer, and soon. But wait, let me tell you about something that sounds like pure fantasy but is absolutely real. There's a planet out there, a world called PSR J1719-1438b, and it's made of diamond. Not mostly diamond. Not diamond-like. Actual crystalline carbon, the same material in the engagement rings and jewelry that humans prize so highly. The planet is about 5 times the size of Earth and orbits a rapidly spinning neutron star, the compressed remnant of a dead star. Under the intense pressure and temperature of this bizarre world, carbon has been compressed into the hardest material in the universe. The planet is essentially a gigantic diamond floating in space, worth more than every economy on Earth combined. And we'll never be able to mine it, never be able to reach it, never be able to touch it. It exists as a reminder that the universe creates wonders we can barely comprehend, treasures we can observe but never possess. And that's not the only diamond world. There's a white dwarf star called BPM 37093, also known as Lucy after the Beatles song, that may contain a diamond the size of the moon in its core. 10 billion trillion carats, compressed by the gravitational collapse of a dying star. The universe makes our most precious gemstones look like cheap glass by comparison. Now let's turn to something closer to home, something that changed our understanding of our own cosmic neighborhood. In October 2017, an astronomer named Robert Warwick was examining data from the Pan-STARRS telescope in Hawaii when he noticed something impossible. An object moving through our solar system at 196,000 miles per hour, far too fast to have originated from around our sun. It had come from interstellar space, from another star system, and was passing through our cosmic neighborhood like a traveler on an ancient highway. They named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. Oumuamua was strange. Deeply, profoundly strange. It wasn't round like an asteroid or fuzzy like a comet. Observations suggested it was shaped like a cigar or perhaps a flat disk, 10 times longer than it was wide, about 400 meters long and only 40 meters thick. Nothing in our solar system looks like that. Even stranger, it was tumbling through space, rotating every 7 hours, and it was strangely shiny, reflecting light as if it were coated in metal or ice. Then came the real mystery. As Oumuamua sped away from the sun, it accelerated slightly, pushed by some invisible force. Comets do this because they release gas and dust that acts like a thruster, but Oumuamua showed no tail, no cloud of debris, nothing visible that could be pushing it. For years, scientists debated what Oumuamua could be. Some suggested it was a nitrogen iceberg from a Pluto-like world, broken off by an ancient collision and wandering the galaxy for hundreds of millions of years. Others proposed it was a hydrogen-rich comet that had been bombarded by cosmic rays during its interstellar journey, trapping hydrogen in its ice that was released as it warmed near the sun. A few, including a Harvard astronomer, suggested something more controversial, that it might be artificial, a solar sail built by an alien civilization, though this idea was widely criticized as speculative and unlikely. The truth is, we'll probably never know for certain. Oumuamua is now beyond Neptune's orbit, speeding away from us, beyond the reach of any telescope. It came as a messenger, showed us something we'd never seen before, and left us with more questions than answers. But here's what Oumuamua taught us. We are not alone in our solar system. Not in the sense of alien intelligence, but in the sense that interstellar objects pass through regularly, visitors from other star systems that formed around other suns. Astronomers now estimate that at any given time, there might be 10,000 Oumuamua-sized objects within Neptune's orbit. We just never noticed them before because we didn't have the technology to detect such small, fast-moving objects. In 2019, we detected our second interstellar visitor, a comet called Borisov, which looked more like a traditional comet with a tail and coma. And there will be more. Future telescopes like the Vera Rubin Observatory will detect dozens, perhaps hundreds of these interstellar travelers, giving us a cosmic census of what exists in the space between stars, fragments, and outcasts from distant planetary systems. Think about this for a moment. Every one of these objects has a history. Oumuamua was born in some distant solar system billions of years ago. It orbited its sun, perhaps alongside planets where life might have evolved. Then something happened. Maybe a giant planet's gravity kicked it out. Maybe its star died in a supernova explosion. Maybe a collision shattered its parent body. For hundreds of millions of years, Oumuamua drifted through the endless void between stars, frozen and alone, until by pure chance it passed through our solar system. It saw our sun, our planets, the world where you were born, and then it left, continuing its eternal journey to nowhere. That's the reality of space. Most objects are wanderers, orphans, cast out from their homes and doomed to drift forever through the emptiest parts of the universe. Now let me take you to the very edge of what we can see, to the earliest moments of cosmic history. The James Webb Space Telescope, launched on Christmas Day 2021, has revolutionized our understanding of the early universe. This telescope doesn't orbit Earth like Hubble. It sits 1.5 million kilometers away, at a gravitational balance point between Earth and the Sun, protected by a 5-layer sunshield the size of a tennis court that keeps its instruments at -233 degrees Celsius. And what it's seeing is rewriting textbooks. Webb has discovered galaxies that existed just a few hundred million years after the Big Bang, when the universe was only 2% of its current age. These shouldn't exist. According to our models, galaxies need time to form, time for dark matter to clump together, time for hydrogen and helium to collapse and ignite into stars. But there they are, bright and massive and impossible. Some of these early galaxies are producing stars at rates that make our Milky Way look lazy. Others contain supermassive black holes millions of times the mass of our Sun, grown to impossible sizes in impossible time frames. It's as if the early universe was in a hurry, building structures faster than physics should allow. Webb has found what astronomers are calling little red dots, mysterious objects that might not be galaxies at all but something entirely new, possibly black hole stars, objects that blur the line between stars and black holes in ways we don't understand. It's discovered water vapor on exoplanets, detected complex organic molecules in distant nebulae, and captured images of planets forming around young stars in ways we've never seen before. The telescope has given us a glimpse of a cosmic dawn that's stranger and more complex than we predicted. But perhaps Webb's most profound discovery is this. The universe's very first galaxies look nothing like what our simulations predicted. They're too bright, too mature, too organized. Either our models of galaxy formation are fundamentally wrong, or something happened in the early universe that we don't understand, some process or force that accelerated cosmic evolution. This is how science advances, not by confirming what we expect, but by showing us where we're wrong, forcing us to rethink everything we thought we knew. Let's talk about something that exists in our own solar system, hiding beneath the ice of distant moons. In 1995, NASA's Galileo spacecraft made a discovery that changed the search for extraterrestrial life forever. Jupiter's moon Europa, a world slightly smaller than Earth's moon, has an icy surface covered in cracks and ridges that suggest something remarkable. Beneath that ice, perhaps 10 to 15 miles down, there's an ocean. A liquid water ocean that might be up to 60 miles deep and contain more than twice as much water as all of Earth's oceans combined. And it's been there for billions of years, kept liquid by the tidal forces of Jupiter's massive gravity, which flex and heat Europa's interior like a cosmic heating pad. But Europa isn't alone. Saturn's tiny moon Enceladus, barely 300 miles in diameter, is even more exciting. In 2005, the Cassini spacecraft detected enormous plumes of water vapor shooting from cracks near Enceladus's south pole, geysers of liquid water erupting into space from an ocean hidden beneath miles of ice. These plumes contain not just water but complex organic molecules, the building blocks of life. Scientists have detected salts and silicates, evidence that the ocean is in contact with a rocky core where chemical reactions could provide energy for life. The ocean of Enceladus is warm, possibly heated by volcanic vents similar to those on Earth's ocean floor, where unique ecosystems thrive in total darkness, fed not by sunlight but by chemical energy from the planet itself. Think about what this means. On Earth, wherever we find liquid water, we find life. In the boiling pools of Yellowstone, in the frozen lakes beneath Antarctic ice, in the crushing pressure of the deepest ocean trenches, life adapts, survives, thrives. If Europa and Enceladus have had liquid oceans for billions of years, oceans rich in organic chemistry and energy sources, then the question isn't whether life could exist there. The question is, how could it not? These moons might harbor entire ecosystems that have evolved completely independently from Earth, life forms that developed in eternal darkness, that have never seen a sunrise, that exist in ways we can barely imagine. And we could find them. Future missions are being planned to Europa and Enceladus, spacecraft that will analyze those water plumes, perhaps even drill through the ice, searching for the unambiguous signature of biology. The discovery of life in our own solar system, even simple microbial life, would prove that life is not unique to Earth, that the universe is filled with biology waiting to be discovered. Now let me tell you about dark energy, perhaps the most disturbing discovery in all of science. In the 1990s, two independent teams of astronomers were studying distant supernovae, stellar explosions so bright they can outshine entire galaxies. They were using these supernovae as cosmic measuring sticks to map the expansion of the universe. Everyone expected to find that gravity was slowing down the universe's expansion, that billions of years from now, the universe might even stop expanding and begin to contract. What they found instead was terrifying. The universe isn't just expanding, it's accelerating. The expansion is speeding up, driven by some unknown force that pervades all of space, a force that acts like anti-gravity, pushing galaxies apart faster and faster. They called it dark energy. Here's the truly disturbing part. Dark energy makes up 68% of the universe. Everything we can see, all the stars and galaxies and planets and gas clouds, all the normal matter made of atoms, makes up only 4% of the universe's total mass and energy. 4%. The rest is dark energy and dark matter, substances we cannot see, cannot touch, cannot understand. We live in a universe where we comprehend less than 5% of what exists. The rest is mystery, governed by physics we don't understand, made of substances we can't detect except through their gravitational effects. What is dark energy? We don't know. Is it a property of space itself, an inherent energy woven into the fabric of reality? Is it a new field like a cosmic fluid that fills the universe? Is it evidence that our understanding of gravity is incomplete, that Einstein's equations need revision? We don't know, but we can predict its future. If dark energy continues to accelerate the universe's expansion, then trillions of years from now, galaxies will be so far apart that no light from one will ever reach another. Future civilizations, if they exist, will look at the night sky and see nothing but darkness, isolated in a lonely bubble of space with no evidence that anything exists beyond their own galaxy. They will think they are alone in a static universe, never knowing the truth. Eventually, the acceleration will become so extreme that even atoms themselves will be torn apart in what scientists call the Big Rip. The universe will end not in a gentle fade, but in a violent tearing of the fundamental fabric of matter itself. That's the future dark energy promises. A universe that dies in isolation and destruction. But let's return to something more immediate, more tangible. In April 2019, the world saw something that had been theorized for over a century but never observed. A photograph of a black hole. Not an artist's impression. Not a simulation. An actual photograph. The image showed a bright ring of glowing gas surrounding a dark circle, the shadow of a supermassive black hole at the center of a galaxy called Messier 87, 55 million light-years from Earth. The black hole is 6.5 billion times more massive than our Sun, and its event horizon, the point of no return where even light cannot escape, is larger than our entire solar system. To capture this image, scientists created a virtual telescope the size of the entire Earth, combining data from radio telescopes spread across the planet, from Hawaii to Chile to the South Pole. They collected petabytes of data, so much information that it couldn't be transmitted over the internet, but had to be physically flown on hard drives to a central processing facility. And then they had to develop entirely new algorithms and mathematical techniques to turn that data into an image. The result was worth it. For the first time, humanity saw direct visual proof of one of the universe's most extreme objects, a region of space-time so warped that it creates a one-way barrier around itself, a cosmic trap from which nothing, not even light itself, can escape. But that wasn't the only black hole we photographed. In May 2022, the same team released an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy, just 27,000 light-years from Earth. This black hole is much smaller, only 4 million times the mass of the Sun, but it's surrounded by the same bright ring of glowing gas. And here's something that should make you pause. That black hole is at the center of our galaxy. Earth orbits the Sun. The Sun orbits the galactic center, completing one orbit every 230 million years. We are in orbit around a black hole. Not a close orbit, thank the laws of physics. We're safe at our distance. But we are, in a very real sense, gravitationally bound to one of the most destructive objects in the universe. Recent observations have revealed even more astonishing things. Astronomers have detected runaway black holes, supermassive black holes that have been kicked out of their galaxies, possibly by the gravitational recoil from merging with other black holes. One such black hole is traveling through space at 2.2 million miles per hour, trailing a wake of newly formed stars behind it like a cosmic speedboat. Another discovery found magnetic fields spiraling around Sagittarius A star in patterns that suggest it might have a hidden jet, a beam of particles and energy shooting out at nearly the speed of light, something we didn't expect to see. The universe's black holes are not just gravitational monsters. They're dynamic, they're active, they're reshaping the cosmos around them in ways we're only beginning to understand. Let's talk about a discovery that challenges our very definition of what a planet is. In 1995, astronomers Michel Mayor and Didier Queloz announced something extraordinary. They had detected a planet orbiting a sun-like star beyond our solar system. The planet, called 51 Pegasi b, was enormous, about half the mass of Jupiter, and it orbited its star in just 4 days, far closer than Mercury orbits our Sun. This was the first confirmed detection of an exoplanet around a normal star, and it opened the floodgates. We now know of over 5,000 confirmed exoplanets, with thousands more candidates waiting for confirmation. And they come in varieties we never imagined. There are hot Jupiters, massive gas giants that orbit so close to their stars that their atmospheres are boiling away, with surface temperatures exceeding 3,000 degrees Fahrenheit, where clouds are made of vaporized rock and it rains liquid iron. There are super-Earths, rocky planets larger than Earth but smaller than Neptune, a planet type that doesn't exist in our solar system and challenges our theories of how planets form. There are ocean worlds like K2-18b, worlds that might be covered entirely in liquid water. There are rogue planets, wandering through interstellar space unattached to any star, frozen and dark. There are planets orbiting binary star systems, worlds with 2 suns in their sky like something from science fiction. There's even a planet orbiting the closest star to our Sun, Barnard Star, just 6 light-years away, a world we might someday be able to visit with advanced spacecraft. The most common type of planet we've discovered is the super-Earth, rocky worlds between 1.5 and 2 times Earth's mass. These planets are everywhere in the galaxy, but we don't have one in our solar system, which raises a profound question. Is our solar system typical or unusual? Are we living in a cosmic oddity, a planetary arrangement that's rare in the universe? The discovery of exoplanets has forced us to realize that our home system might not be the template for how planets form. The universe has more variety, more creativity than we ever suspected. And here's what keeps astronomers up at night. If planets are so common, if every star has them, if there are trillions of planets in our galaxy alone, then where is everybody? Where are the alien civilizations? Where are the radio signals, the megastructures, the signs of intelligence? This is the Fermi paradox, the contradiction between the high probability of alien civilizations and the complete absence of evidence for them. Are we truly alone, the only intelligence in a galaxy of trillions of worlds? Or are civilizations so short-lived that they destroy themselves before they can spread? Or perhaps intelligence is so rare, so unlikely, that despite all those planets, we are the universe's first attempt at self-awareness. We don't know, and that uncertainty is both thrilling and terrifying. Now let me take you to the realm of the truly bizarre, to discoveries that seem to violate the laws of physics themselves. Fast radio bursts, or FRBs, are one of the most mysterious phenomena in astronomy. In 2007, astronomers analyzing old data from the Parkes radio telescope in Australia discovered a burst of radio waves lasting just a few milliseconds, but containing as much energy as the sun emits in an entire day. The burst came from a distant galaxy billions of light years away. Since then, thousands of FRBs have been detected, some repeating, others appearing only once and never again. What causes them? We don't know for certain. The leading theory is that they're produced by magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, so powerful that the magnetic field itself distorts the vacuum of space. When something disturbs a magnetar, perhaps a starquake or a sudden rearrangement of its crust, it can release a burst of energy that beams across the universe like a cosmic lighthouse. But some FRBs don't fit this explanation. Some seem to come from interactions between neutron stars and companion stars, others from completely unknown sources. We're detecting these bursts at a rate of about 1,000 per day across the entire sky, which means somewhere in the universe, every single day, 1,000 events so energetic they outshine entire galaxies and radio waves are occurring. The universe is far more violent and active than the peaceful night sky suggests. Then there's the discovery of phosphine on Venus. In September 2020, scientists announced they had detected phosphine gas in Venus's atmosphere, a compound that on Earth is only produced by anaerobic bacteria or industrial processes. The discovery was controversial from the start. Some scientists questioned whether the detection was real or an artifact of the data processing. Others proposed alternative chemical pathways that could produce phosphine without biology, involving sulfur compounds and atmospheric chemistry unique to Venus's hellish environment. The debate continues, a reminder that claims of biosignatures must be extraordinarily rigorous, that we cannot afford to be hasty when declaring we found evidence of life. But whether phosphine on Venus is biological or not, the controversy highlights something important. We now have the technology to detect chemicals in planetary atmospheres, to analyze worlds so hostile that no spacecraft could survive on their surface, to search for the unexpected. Venus, with its surface temperature hot enough to melt lead and atmospheric pressure 90 times greater than Earth's, seemed like the last place we'd look for life. Yet here we are, debating whether microbes might exist in its cloud layer, floating in droplets of sulfuric acid, surviving in an environment that would destroy any Earth organism in seconds. Life, if it exists, might be far more adaptable and resilient than we ever imagined. Let's return to the realm of the spectacularly large, to discoveries about the structure and fate of the universe itself. The cosmic microwave background, or CMB, is light from the very beginning of time, photons that have been traveling through space for 13.8 billion years, since just 380,000 years after the Big Bang. This light has been stretched by the expansion of the universe, redshifted from visible light into microwave radiation, and it fills every cubic centimeter of space with a faint glow at a temperature of 2.7 degrees above absolute zero. Satellites like WMAP and Planck have mapped this ancient light in exquisite detail, and what they've found is remarkable. The CMB is almost perfectly uniform, the same temperature in every direction to within 1 part in 100,000. But there are tiny fluctuations, regions slightly hotter or colder than average, and these fluctuations are the seeds of everything that exists. Regions that were slightly denser attracted more matter through gravity, eventually collapsing to form the first stars and galaxies. The pattern of these fluctuations tells us the age of the universe, its composition, its expansion rate, and its ultimate fate with incredible precision. But the CMB also contains mysteries. There's a feature called the cold spot, a region much larger and colder than statistical fluctuations should allow. Some scientists have proposed it might be evidence of another universe colliding with ours in the distant past, a remnant of cosmic violence on scales we can barely comprehend. Others suggest it's just a statistical anomaly, a cosmic coincidence. We don't know, and that's unsettling, because the CMB is supposed to be our most reliable record of the early universe, the one thing we thought we understood completely. Now let me tell you about the Higgs boson, often called the God particle, though physicists hate that name. In July 2012, after decades of searching and billions of dollars spent on the Large Hadron Collider in Switzerland, scientists announced they had discovered it. The Higgs boson is a particle that emerges from the Higgs field, an invisible field that permeates all of space and gives other particles their mass. Without the Higgs field, electrons would have no mass, atoms couldn't form, chemistry would be impossible, and you wouldn't exist. Think about that for a moment. There's an invisible field surrounding you right now, passing through your body, through every atom, giving those atoms the property we call mass, making them resist acceleration, making them fall in gravity. Without it, the universe would be nothing but massless particles zipping around at the speed of light, incapable of forming structures, incapable of creating the complexity needed for life. The Higgs field is what allows matter to exist in the form we recognize. It's the reason you have weight, the reason things fall when you drop them, the reason the universe is anything other than an empty void of light. And we've detected the particle that proves this field exists, confirming one of the most profound predictions in all of physics. But here's what keeps physicists awake at night. The Higgs field has a problem. Its energy density, according to our calculations, should be enormous, so large that it would cause the universe to collapse or expand far faster than it does. Yet it doesn't. The field seems to be in a delicate balance, fine-tuned to a value that allows the universe to exist. Why? Is there some deeper principle we're missing? Is our universe one of countless others in a multiverse, and we happen to exist in one where the Higgs field has the right value for life? Or is there new physics, new forces and particles we haven't discovered yet that stabilize the field? We don't know, and that ignorance is profound. Let's talk about something happening in our solar system right now. Discoveries from missions that are exploring worlds we thought we understood. The Sun, our life-giving star, has mysteries that scientists are only now unraveling. In 2024, the European Space Agency's solar orbiter made a groundbreaking discovery. It flew through the magnetic field connected to a coronal hole, a dark region on the Sun's surface where magnetic field lines stretch out into space. For the first time, scientists watched in real time as the solar wind, the stream of charged particles that flows from the Sun at hundreds of kilometers per second, changed speed from fast to slow as it passed through different regions. They could trace the wind back to specific features on the Sun's surface, solving a decades-old mystery of how the solar wind is generated. This matters because the solar wind is what creates the beautiful auroras that dance in Earth's polar skies, the northern and southern lights. It's also what can destroy satellites, disrupt power grids, and threaten astronauts in space during solar storms. Understanding how the Sun produces this wind, how it varies and accelerates, helps us predict space weather and protect our increasingly vulnerable technological civilization. But the discoveries keep coming. Scientists have found that the sun's magnetic field creates phenomena we never predicted, structures and instabilities that challenge our models. The sun, after billions of years of study, is still teaching us, still surprising us. Mars has yielded discoveries that change how we view the possibility of ancient life in our solar system. NASA's rovers, from Spirit and Opportunity to Curiosity and Perseverance, have found overwhelming evidence that Mars was once a warm, wet world with lakes, rivers, and possibly even an ocean covering much of its northern hemisphere. They found clay minerals that can only form in the presence of water, ancient lake beds with sedimentary layers showing how water levels rose and fell over millions of years, and organic molecules, the building blocks of life, preserved in rocks billions of years old. But Mars's water disappeared. The planet's weak gravity and lack of a global magnetic field allowed the solar wind to strip away its atmosphere over billions of years. As the atmosphere thinned, liquid water could no longer exist on the surface. It either froze or evaporated into space. Today, Mars is a frozen desert, with temperatures averaging -80 degrees Fahrenheit and an atmosphere so thin it's nearly a vacuum. But in 2024, seismic data from NASA's InSight lander revealed something extraordinary. Deep beneath Mars's surface, there might be a vast reservoir of liquid water, enough to fill oceans on the planet's surface if it were released. This water is trapped in porous rock, kept liquid by the heat and pressure of the planet's interior. If microbes evolved on ancient Mars when it was habitable, could they have retreated underground as the surface became inhospitable? Could there still be life on Mars, not on the surface but deep below, surviving in these hidden aquifers? Future missions might drill down to find out, searching for the most profound discovery in human history, proof that life arose independently on another world. Let me tell you about Pluto, the distant world that captured our hearts. When NASA's New Horizons spacecraft flew past Pluto in July 2015, it revealed a world of breathtaking beauty and complexity. Scientists expected a dead, cratered ball of ice. Instead, they found a geologically active world with towering mountains made of water ice as hard as rock, vast plains of nitrogen ice that flow like glaciers, a thin atmosphere of nitrogen and methane that can freeze and snow onto the surface, and a gigantic heart-shaped region now called Tombaugh Regio that became an instant icon. Most remarkably, Pluto is too small and too cold to have significant internal heat from radioactive decay. It shouldn't be geologically active, yet it is. Something is driving activity on this tiny world at the edge of the solar system. Possibly tidal heating from its large moon Charon, possibly heat from the decay of radioactive elements we haven't yet identified. The discovery forced scientists to realize that even small, distant, frozen worlds can be dynamic and complex, that we've underestimated the diversity and activity of objects in our solar system. Now let's venture to the realm of pure strangeness, to discoveries that make no sense according to conventional physics. Astronomers have discovered dark galaxies, collections of gas and possibly dark matter that seem to contain no stars at all. A galaxy, by definition, is a collection of stars bound together by gravity. But these objects have all the mass and structure of a galaxy without the stars. How is that possible? We don't know. Do they represent a phase in galaxy evolution we've never observed? Are they dominated by dark matter to such an extent that normal matter can't collapse to form stars? Are our definitions of what constitutes a galaxy fundamentally wrong? The discovery challenges our understanding of how galaxies form and evolve. Then there are quasi-stars, theoretical objects that might have existed in the early universe. These would have been massive stars with a black hole at their core, the black hole feeding on the star from the inside out, creating an object thousands of times larger and more luminous than any star should be. We've never definitively observed one, but some of the mysterious bright objects Webb is detecting in the early universe might be quasi-stars, hybrid objects that blur the line between stars and black holes. If they existed, they could explain how supermassive black holes grew so large so quickly in the early universe, feeding on the very stars they were born inside. Let's talk about magnetars, neutron stars with magnetic fields so intense they defy comprehension. A magnetar's magnetic field is about a quadrillion times stronger than Earth's. At a distance of 1,000 kilometers, the field is strong enough to distort the electron clouds in atoms, making chemistry impossible. If you got within 1,000 kilometers of a magnetar, the magnetic field would fatally disrupt the bioelectrical currents in your nervous system, killing you instantly. It would also scramble the quantum states of atoms in your body, literally disassembling you at a molecular level. Magnetars occasionally undergo starquakes, where their crust suddenly cracks and rearranges. When this happens, they release bursts of X-rays and gamma rays so intense they can be detected across the galaxy. In December 2004, a magnetar called SGR 1806-20 released a burst so powerful it affected Earth's atmosphere from 50,000 light-years away, ionizing the upper atmosphere and causing a measurable change in the planet's magnetic field. That's the power we're dealing with. An object the size of a city, releasing more energy in a fraction of a second than the sun emits in a year. And neutron stars themselves are bizarre. They're the remnants of massive stars that exploded as supernovae, their cores compressed by gravity until protons and electrons merge to form neutrons, creating matter so dense that a teaspoon would weigh 1 billion tons. The gravity at the surface is so intense that if you dropped an object from 1 meter above the surface, it would hit the ground at a significant fraction of the speed of light, releasing energy equivalent to a nuclear bomb. The star's spin can be absurdly fast, some pulsars rotating hundreds of times per second, their surfaces moving at a significant fraction of light speed. Inside a neutron star, matter exists in phases we can barely understand. The outer crust is made of atomic nuclei crushed together in a crystal lattice. Deeper down, neutrons form a superfluid, flowing without friction. At the core, matter might break down into its constituent quarks, creating quark matter in states we can only study theoretically. Neutron stars are laboratories of extreme physics, places where the laws of nature are tested to their breaking point. Let me tell you about the multiverse, a hypothesis that makes some scientists uncomfortable but seems increasingly difficult to avoid. The idea is this: our universe, with its specific laws of physics and constants of nature, might be just one of countless universes, each with different properties. Some universes might have stronger gravity, making stars burn faster and preventing complex chemistry. Others might have no dark energy, causing them to collapse soon after the Big Bang. Most universes might be utterly hostile to life, empty voids where nothing interesting ever happens. This idea arises from inflation, the theory that the early universe underwent a period of exponential expansion. If inflation happened once, it could happen again and again, creating bubble universes disconnected from our own. It also arises from string theory, which predicts a vast landscape of possible universes, each with different configurations of extra dimensions and forces. And it arises from quantum mechanics, where every quantum decision creates a branching timeline, a separate universe where the other outcome occurred. If the multiverse is real, it would explain why our universe seems so finely tuned for life. It's not that someone designed the universe for us. It's that we exist in one of the rare universes where the constants of nature allow for stars, planets, and life. In other universes, no one is there to ask why. This is called the anthropic principle, and it's controversial because it seems to give up on finding a deeper explanation for why our universe has the properties it does. But it might be true nonetheless, a humbling reminder that even our entire observable universe might be just one grain of sand on an infinite cosmic beach. Now let's talk about cosmic strings, theoretical defects in space-time that might have formed in the early universe. Imagine the fabric of space itself having a flaw, a one-dimensional object thinner than an atom but stretching across light years, with a mass so enormous that it warps space-time around it. If a cosmic string passed between you and a distant star, you would see two images of that star, space-time bent around the string like light bending around a lens. We've never definitively detected a cosmic string, but astronomers are searching for them, looking for telltale patterns in how light from distant galaxies is distorted. If they exist, they would be remnants from the universe's birth, phase transitions in the early cosmos that left scars in the fabric of reality itself. And then there are primordial black holes, tiny black holes that might have formed in the first moments after the Big Bang, not from collapsing stars but from regions of space that were dense enough to collapse directly into black holes. These could be as small as an atom but as massive as a mountain, and they could be everywhere, passing through the solar system, through your body, invisible and undetectable except through their gravitational influence. Some scientists have speculated that primordial black holes could be the dark matter we've been searching for, the invisible mass that holds galaxies together. We don't know if they exist, but the universe has already surprised us so many times that ruling them out seems premature. Let me tell you about the Great Attractor, a gravitational anomaly pulling our galaxy and hundreds of thousands of others toward a region of space in the constellation Hydra Centaurus. We can't see it directly because it lies behind the Milky Way's galactic plane, obscured by dust and stars. But we can measure its pull, a force so strong it's dragging the Milky Way at over 2 million kilometers per hour. What is it? Probably a massive concentration of galaxies, a supercluster containing tens of thousands of galaxies and the mass of tens of thousands of Milky Ways. But we can't be certain because we can't see through the obscuring dust. It's a reminder that even after centuries of astronomy, there are massive structures in our own cosmic neighborhood we know almost nothing about. Let's talk about the future, about what these discoveries mean for humanity's place in the universe. We now know that the ingredients for life are common. Water exists throughout the solar system and beyond. Organic molecules, the building blocks of life, are everywhere we look, in comets, in interstellar gas clouds, in the atmospheres of planets. Stars are ubiquitous, and most of them have planets. Habitable environments might be abundant. If life is common, if it arises wherever conditions allow, then the universe might be teeming with biology. Most of it would be simple, microbial. But some of it might be complex. Some of it might be intelligent. Some of it might be far more advanced than us, with civilizations billions of years old that have solved problems we can't even imagine. But we haven't found them. The universe seems silent, and that silence is perhaps the most disturbing discovery of all. Are we alone? Are we early? Are we in a cosmic desert, one of the first civilizations to arise in a universe that will eventually fill with intelligence? Or are we late, living in the ruins of civilizations that destroyed themselves? Cautionary tales written in the stars. We don't know. But the search continues. SETI, the search for extraterrestrial intelligence, scans the sky for signals from alien civilizations. Future telescopes will analyze the atmospheres of distant planets, searching for industrial pollution, signs of artificial light, evidence of megastructures and technology. And what will happen if we find them? What will we do the day we detect an unmistakable signal from another intelligence? Proof that we are not alone. Will it unite humanity, give us perspective on our petty conflicts and differences? Or will it terrify us, make us realize how vulnerable we are, how young and fragile our civilization is? These are questions we might have to answer in our lifetimes. The discovery could come tomorrow or in 100 years, but it's coming. The universe is too vast, too old, too full of potential for us to be the only ones looking up at the stars and wondering. Consider this. You live in the most extraordinary time in human history. You have the privilege, the cosmic luck, to be alive when humanity is making these discoveries, when we're answering questions that philosophers and dreamers have pondered for millennia. You're alive when we photographed a black hole for the first time, when we detected gravitational waves from colliding black holes, when we found potential signs of life on a distant planet, when we watched the universe reveal itself to be stranger, more violent, more beautiful than anyone imagined. Future generations will look back at this era with envy, wishing they could have experienced the excitement of discovery, the thrill of seeing these cosmic mysteries unfold in real time. But here's the truth that should keep you awake at night. For all we've discovered, for all we've learned, we still understand less than 5% of what the universe is made of. The rest is dark matter and dark energy, mysterious substances we can barely detect and can't explain. We don't know how the universe began or how it will end. We don't know if we're alone or surrounded by life. We don't know if there are other universes beyond our own. We don't know what consciousness is or why we're capable of pondering these questions at all. We stand on the shore of an infinite ocean of ignorance, having explored just the tiniest fraction of the cosmos, and every answer we find reveals a dozen new questions. Think about the Voyager spacecraft, launched in 1977, now beyond the edge of our solar system, traveling through interstellar space at 17 kilometers per second. They carry golden records, messages from humanity to any civilization that might find them, etched with sounds and images from Earth. Music and laughter and greetings in dozens of languages. In tens of thousands of years, they might pass near another star system. In millions of years, they might be found by explorers from a civilization we can't imagine. Or they might drift forever through the void, silent monuments to a species that dared to reach beyond its home world, that looked up at the stars and decided to send a message, even knowing it might never be received. That's what these discoveries represent. They're not just facts and data and observations. They're humanity's message to the universe. We are here. We are looking. We are listening. We are trying to understand. And every discovery, every breakthrough, every mystery solved, and every new question raised is proof that we haven't given up, that we're still reaching out, still exploring, still daring to ask the biggest questions existence has to offer. The universe is vast and ancient and indifferent to our existence. But we persist. We build telescopes and spacecraft. We do the mathematics and the physics. We peer into the deepest darkness and the earliest moments of time, searching for answers. And maybe that's what it means to be human in this cosmic age. Not to have all the answers, but to keep asking the questions. To look at a distant planet and wonder if something there looks back at us. To detect a gravitational wave and marvel that we can hear the universe's most violent events. To photograph a black hole and confront the reality of objects so extreme they bend space and time around themselves. To find organic molecules in interstellar gas clouds and realize that the ingredients of life are woven into the fabric of the cosmos itself. To discover that our galaxy orbits a supermassive black hole and feel the vertigo of our cosmic insignificance and significance simultaneously. So here's what I want you to remember. Tonight, when you look up at the stars, you're not just seeing distant points of light. You're seeing galaxies that might contain trillions of planets, some of which might harbor life. You're seeing the afterglow of the Big Bang, stretched into invisibility but still there, filling every cubic centimeter of space with photons from the universe's birth. You're being bathed in neutrinos from the sun, trillions of them passing through your body every second, ghostly particles that barely interact with matter. You're being stretched and squeezed by gravitational waves from collisions happening billions of light years away. Your atoms dancing to the rhythm of the universe's most violent events. You are not separate from the cosmos. You are part of it. The atoms in your body were forged in the cores of dying stars, scattered across space in supernova explosions, and billions of years later assembled into the planet where you were born and the body you inhabit. You are made of stardust, not metaphorically but literally. The iron in your blood, the calcium in your bones, the carbon in your DNA, all of it was created in stellar furnaces and cosmic explosions. You are the universe made conscious, matter organized in such a way that it can look back at itself and ask questions about its own existence. And here's the final truth, the one that makes all of this matter. These discoveries, these 30 amazing revelations about the cosmos, they're not the end of anything. They're just the beginning. We're living in the early days of cosmic exploration, the first tentative steps of a species that's just starting to understand its place in the universe. Future generations will make discoveries that dwarf everything we've learned so far. They'll visit the oceans of Europa and Enceladus, searching for alien life. They'll send probes to other star systems, confirming or denying the existence of life on planets like K2-18b. They'll detect gravitational waves from the Big Bang itself, probing the universe's first moments. They'll build telescopes that can image the surfaces of planets around distant stars, searching for cities and signs of civilization. They'll answer questions we haven't even thought to ask yet. But this moment, right now, is ours. This is our time to witness the universe revealing itself, to live in the age of discovery when humanity took its first real steps toward understanding the cosmos. This is when we learn to listen to space-time itself, to photograph the unseeable, to analyze the chemical makeup of worlds dozens of light years away, to peer into the universe's earliest moments and farthest reaches. This is when we discovered that we might not be alone, that life might be common, that the universe might be filled with oceans and atmospheres and chemistry and biology waiting to be discovered. So the next time you look up at the night sky, remember this. You're not just seeing stars. You're seeing a universe in motion, a cosmos evolving and changing and creating and destroying on scales that beggar comprehension. You're seeing the past, because light takes time to travel, meaning you're looking at stars as they were years or centuries or millennia ago. You're seeing the future, because those stars will eventually die, some in quiet fades, others in violent explosions that will forge new elements and scatter them across space to form new stars and planets and perhaps new life. You're seeing mystery and wonder and terror and beauty all mixed together, a universe that doesn't care whether you understand it but rewards those who try. And maybe, just maybe, somewhere out there in that vast cosmic ocean, on a planet orbiting a distant star, someone is looking back at you, wondering the same things you're wondering, asking the same questions, marveling at the same mysteries. If they exist, they're your cosmic siblings, being shaped by the same laws of physics, made of the same elements, asking themselves what it all means. And perhaps one day, if we don't destroy ourselves, if we survive long enough, we'll meet them. We'll share what we've learned. We'll compare our discoveries and our questions and realize that despite the vast distances and different origins, we're all children of the same universe, all participants in the same cosmic story. That's what these discoveries mean. They're not just facts to memorize or wonders to passively observe. They're invitations to participate in something larger than yourself, to be part of humanity's ongoing conversation with the cosmos. Every time you learn about a black hole or a distant planet or a gravitational wave, you're connecting with the deepest questions existence has to offer. You're engaging with the same mysteries that have captivated humans since we first looked up at the night sky and wondered what those lights were. So keep looking up. Keep asking questions. Keep marveling at the strangeness and beauty and terror of the universe we inhabit. Because this is your inheritance as a human being in the 21st century. This knowledge that previous generations could only dream of. You know things that kings and philosophers and scientists throughout history would have given anything to learn. You live in a time when the universe is revealing its secrets at an unprecedented pace, when new discoveries arrive so frequently we can barely process them all. And the most amazing thing, we're just getting started. The discoveries yet to come will make today's revelations seem quaint. The questions we'll answer in the coming decades and centuries will reshape humanity's understanding of reality in ways we can't yet imagine. We stand at the edge of an infinite frontier, armed with mathematics and physics and an insatiable curiosity about how the universe works. The cosmos is vast and old and full of wonders we haven't even glimpsed yet. And we're out here, exploring it, one discovery at a time, refusing to be satisfied with ignorance, demanding answers even when those answers reveal how much we still don't understand. That's the human story. That's your story. You're part of the generation that's living through the most extraordinary age of discovery in history. Don't waste it. Don't take it for granted. Look up at those stars and remember that you're looking at your cosmic ancestry, at the furnaces that created your atoms, at the future homes of humanity if we survive long enough to reach them. Remember that you're made of stardust, that you're the universe experiencing itself, that your ability to wonder about these things is perhaps the most extraordinary phenomenon in all of existence. A collection of atoms, organized just right, capable of contemplating infinity, capable of understanding mathematics and physics, capable of building machines that can detect gravitational waves and photograph black holes and analyze the atmospheres of distant worlds. You are a miracle. The universe is a miracle. And the fact that you can sit here in this moment and understand even a fraction of these discoveries is a testament to the power of human curiosity and intelligence and determination. So treasure this knowledge. Share it with others. Let it change how you see the world and your place in it. Because these 30 discoveries are not just information. They're transformation. They're proof that the universe is stranger and more wonderful than we ever imagined, and that we, against all odds, are capable of understanding it. The cosmos has spoken. It has revealed black holes and gravitational waves, exoplanets and biosignatures, dark energy and neutron stars, interstellar visitors and hidden oceans. It has shown us the very edge of the observable universe and the earliest moments of time. It has demonstrated that we live in an age of wonders, surrounded by mysteries that previous generations could not even have conceived of. And the message is clear. We are not done yet. We are not even close to done. The universe has more to teach us, more to show us, more secrets waiting to be uncovered. So keep looking up. Keep wondering. Keep searching for answers. Because somewhere out there, in the vast darkness between the stars, in the crushing depths of alien oceans, in the warp space around black holes, in the earliest photons from the Big Bang, in the chemical signatures of distant atmospheres, the next discovery is waiting. The next breakthrough that will change everything. The next piece of the cosmic puzzle that will make us rethink who we are and where we came from and where we're going. And you get to be here for it. You get to witness it. You get to be part of humanity's ongoing journey from ignorance to understanding, from isolation to cosmic citizenship. This is your time. This is your universe. These are your discoveries. Make them count. But I'm not finished with you yet. There's so much more to explore, so many more discoveries that will reshape how you understand reality. Let me take you deeper into the cosmic rabbit hole, to revelations so profound they'll make everything I've told you so far seem like a preface. Let's talk about something happening right now, at this very moment. Deep beneath a mountain in Italy, in a laboratory called Gran Sasso, scientists are hunting for dark matter. They've filled enormous tanks with liquid xenon, cooled to -100 degrees Celsius, and they're waiting for a dark matter particle to collide with a xenon atom, to produce a flash of light that would be the first direct detection of the mysterious substance that makes up 27% of the universe. They've been waiting for years, decades, and they've found nothing, absolutely nothing. But the fact that we're even capable of building such experiments, that we can create detectors sensitive enough to catch a single collision from a particle that barely interacts with normal matter, that's extraordinary in itself. What is dark matter? We know what it does. It provides the gravitational glue that holds galaxies together. Without it, stars at the edges of galaxies would fly off into space. The rotation curves of galaxies, the way stars orbit the galactic center, only make sense if there's far more mass than we can see. Galaxy clusters bend light from more distant galaxies in ways that require enormous amounts of invisible mass. The cosmic microwave background shows patterns that only work if dark matter existed in the early universe. We can map it, see its effects, measure how it clumps and flows. But we don't know what it is. The leading candidate is something called a WIMP, a weakly interacting massive particle, a hypothetical particle that has mass but interacts with normal matter only through gravity and possibly the weak nuclear force. These particles would be passing through you right now, billions of them every second, flying through your body, through the earth, barely noticing that ordinary matter exists. But despite decades of searching, we haven't detected one. Other theories propose axions, ultralight particles that form wave-like structures across space, or primordial black holes, tiny black holes from the Big Bang, or modifications to gravity itself, suggesting that our understanding of how gravity works at galactic scales is simply wrong. We don't know. And that's terrifying, because it means the majority of the matter in the universe is made of something we've never seen, never touched, never even identified. Imagine living in a house where you can see only 5% of the rooms, and the rest are hidden behind walls you can't penetrate. That's our situation with the universe. We're fumbling in the dark, trying to understand a cosmos where most of what exists is invisible to us. And yet we persist. We build bigger detectors, more sensitive instruments. We propose new theories and test them. We refuse to accept ignorance as final. Now let me tell you about cosmic inflation, a theory so wild it sounds like science fiction, but is currently the best explanation we have for why the universe looks the way it does. In the first fraction of a second after the Big Bang, roughly 10 to the minus 36 seconds, the universe underwent a period of exponential expansion. Space itself expanded faster than the speed of light, doubling in size every tiny fraction of a second. In less than a billionth of a second, the universe grew from something smaller than an atom to something larger than a galaxy. This sounds impossible. How can anything travel faster than light? But space itself isn't bound by that speed limit. Space can expand or contract at any rate, and during inflation, it expanded faster than anything could traverse it. Why did this happen? The theory proposes a field called the inflaton field, an energy field that dominated the very early universe. When this field was in a high-energy state, it caused space to expand exponentially. Then the field decayed, releasing its energy and creating all the matter and radiation in the universe, the hot Big Bang that we typically associate with the universe's beginning. Inflation solves several major problems in cosmology. It explains why the universe is so uniform, so similar in every direction. Without inflation, different regions of the universe would never have been in contact with each other, so there's no reason they should have the same temperature and density. But if they all came from a tiny region that expanded rapidly, that uniformity makes sense. Inflation also explains why the universe is so flat, so close to the critical density that separates eternal expansion from eventual collapse. It inflates away any curvature that might have existed before. But here's where it gets really strange. If inflation happened once, it might happen again. In fact, according to some versions of the theory, it never stopped. Our observable universe is just one bubble in an eternally inflating multiverse, a cosmos where new universes are constantly being born, each with potentially different laws of physics. Some of these universes might last a fraction of a second before collapsing. Others might expand forever, cold and empty. And a tiny fraction might have conditions suitable for complexity, for stars and planets and life. We happen to exist in one of those rare universes, not because we're special, but because only universes like ours can produce observers who can ask these questions. This is deeply unsettling to many physicists. It suggests that we can never have a complete theory of physics, because the laws we observe in our universe might just be local bylaws, specific to our cosmic bubble. Other universes might have different numbers of dimensions, different fundamental forces, different values for constants like the strength of gravity or the mass of the electron. And if that's true, then many of the questions we're asking, why does the universe have these specific properties, might not have deeper answers. They just are, and we're here to observe them because only universes with these properties can create life. Let me tell you about something even more disturbing. The vacuum of space is not empty. Quantum mechanics tells us that even in what we call a perfect vacuum, particles are constantly popping into existence and disappearing, borrowed from the energy inherent in empty space itself. These are called virtual particles, and they exist for such short times that they don't violate the laws of physics. We've even measured their effects. The Casimir effect, where two metal plates placed very close together in a vacuum experience an attractive force, is caused by virtual particles. The anomalous magnetic moment of the electron, a tiny discrepancy in how electrons behave in magnetic fields, is explained by virtual particles interacting with the electron. But here's the problem. When physicists calculate how much energy should be in the vacuum based on quantum mechanics, they get a number that's 10 to the power of 120 times larger than what we observe. That's not a small error. That's the worst prediction in the history of physics. If the vacuum energy were actually that large, the universe would have exploded into nothingness a fraction of a second after it began. Something is canceling out almost all of this energy, leaving just the tiny amount we observe as dark energy. What? We have no idea. Some mechanism, some symmetry, some principle we don't understand is balancing these energies to a precision of 120 decimal places. Either that, or our entire understanding of quantum mechanics and vacuum energy is fundamentally flawed. This is called the cosmological constant problem, and it's been described as the biggest embarrassment in theoretical physics. We can calculate things. We can measure things. But when we try to connect the calculations to the measurements, we're off by a factor so large it might as well be infinity. And we don't know why. This should keep you awake at night. It means that our two most successful theories, quantum mechanics and general relativity, are giving us answers that make no sense when combined. Something is deeply wrong with our understanding of reality at the most fundamental level. Let's talk about the Big Bang itself, the moment when everything began. Or did it? The Big Bang theory tells us that the universe was once incredibly hot and dense, concentrated in a state of nearly infinite temperature and density. Then it began expanding, cooling as it did so. Within the first few minutes, protons and neutrons formed and fused into the lightest elements, hydrogen and helium. After about 380,000 years, the universe cooled enough for electrons to combine with nuclei, forming neutral atoms, and the universe became transparent to light for the first time. That light is what we see as the cosmic microwave background. But what came before? Was there a before? General relativity suggests that time itself began at the Big Bang, that asking what came before is like asking what's north of the North Pole. It's a meaningless question because time didn't exist. But other theories suggest alternatives. Maybe the Big Bang was a bounce, the universe collapsing and then re-expanding, part of an eternal cycle of birth and death and rebirth. Maybe it was a collision between higher dimensional brains, membranes in a higher dimensional space, and our universe is just a three-dimensional slice of something much larger. Maybe it was the decay of a false vacuum, a transition from one quantum state to another that released enough energy to create everything we see. We don't know, and we may never know, because the very earliest moments of the Big Bang are hidden behind a barrier we cannot penetrate. The Planck epoch, the first 10 to the minus 43 seconds, is a realm where quantum mechanics and gravity merge, where our theories break down and give nonsensical answers. To understand what happened then, we would need a theory of quantum gravity, a way of describing space-time at the smallest scales. We don't have one. String theory, loop quantum gravity, and other approaches are trying, but none of them have made predictions we can test with current technology. So the ultimate question, why is there something rather than nothing, remains unanswered. Why does the universe exist? Why these laws of physics and not others? Why does mathematics work so well at describing reality? These are questions at the boundary of physics and philosophy, and we're nowhere close to answering them. Now let me tell you about quantum entanglement, a phenomenon so strange that Einstein called it spooky action at a distance, and refused to believe it was real. Here's how it works. Take two particles and put them in a quantum state where their properties are correlated. Separate them by any distance, light years if you want. Now measure one particle. Instantly, at the exact same moment, the other particle responds, its properties changing to maintain the correlation. Not through any signal, not through any force, just instantaneously. This has been tested thousands of times. It's real. It happens. And it violates our intuitive understanding of how cause and effect should work. Einstein thought this proved quantum mechanics was incomplete, that there must be hidden variables we weren't seeing, information carried by the particles that determine their behavior. But in the 1960s, physicist John Bell devised a test to check this, and when the experiments were done, they proved Einstein wrong. There are no hidden variables. The correlation really is instantaneous. Measuring one particle really does affect the other, regardless of distance. This doesn't violate relativity because you can't use entanglement to send information faster than light, but it does mean that the universe is fundamentally non-local, that distant events can be connected in ways that defy our normal understanding of space and time. This has led to wild speculation. Does entanglement mean the universe is somehow holographic, that all information about any region of space is encoded on its boundary? Does it mean that space and time themselves emerge from quantum entanglement, that they're not fundamental but derived from deeper quantum connections? We're beginning to explore these ideas, and they're leading us to question whether space and time are real in the way we think they are, or whether they're just useful approximations of something stranger. Let me tell you about supernovae, stellar explosions so bright they can outshine entire galaxies. When a massive star, at least 8 times the mass of the Sun, exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses in less than a second, going from the size of Earth to the size of a city. The outer layers fall inward at a quarter of the speed of light, hit the incompressible neutron core, and rebound in a shockwave that tears the star apart. For a few weeks, that single exploding star can emit as much energy as 100 billion stars. The explosion is so violent it creates elements heavier than iron, forging gold and uranium and platinum in the fireball. These elements are scattered across space, seeding future generations of stars and planets. Every atom of gold in your jewelry, every atom of iron in your blood, every heavy element in your body was created in a supernova explosion billions of years ago. You are literally made from the ashes of dead stars. When Carl Sagan said we are star stuff, he wasn't being poetic. He was being literal. The calcium in your bones, the phosphorus in your DNA, the sulfur in your proteins, all of it was forged in the cores of dying stars and scattered across the galaxy in these cosmic explosions. But supernovae are more than just element factories. They're also cosmic distance markers. A specific type called Type Ia supernovae occur when a white dwarf star, the remnant of a sun-like star, accretes matter from a companion until it exceeds a critical mass and explodes. Because this critical mass is always the same, all Type Ia supernovae have roughly the same intrinsic brightness. This makes them standard candles, objects whose true brightness we know, allowing us to calculate their distance by measuring how bright they appear. It was by studying distant Type Ia supernovae that astronomers discovered dark energy, measuring distances to galaxies billions of light years away and finding that the universe's expansion is accelerating. And here's something fascinating. Supernovae are rare. In a galaxy like the Milky Way, they happen maybe once or twice per century. The last one visible from Earth in our galaxy was in 1604, observed by Johannes Kepler. We're actually overdue for another one. Somewhere in the Milky Way, right now, a massive star might be in its final moments, preparing to explode. When it does, it will be visible in daylight, a new star brighter than Venus, visible for weeks or months. Imagine that. Imagine looking up at the daytime sky and seeing a star bright enough to cast shadows, knowing you're watching a cosmic catastrophe happening in real time. A star dying and scattering its guts across light years of space. Let me tell you about gamma-ray bursts, the most energetic events in the universe since the Big Bang. These are flashes of gamma rays, the highest energy form of light, that last anywhere from milliseconds to several minutes. They were discovered by accident in the 1960s by satellites designed to detect nuclear weapons tests. And for years, astronomers had no idea what they were. Now we know. They're the death cries of the most massive stars in the universe, objects dozens of times more massive than the Sun, collapsing not into neutron stars but into black holes. As the star collapses, jets of material are accelerated to 99.9% of the speed of light, shooting out from the poles of the dying star. If one of these jets happens to be pointed at Earth, we see a gamma-ray burst. The energy released in a gamma-ray burst is staggering. In a few seconds, it can emit as much energy as the Sun will produce in its entire 10 billion year lifetime. If one occurred in our galaxy within a few thousand light years of Earth, and the jet was pointed at us, it would be catastrophic. The gamma rays would strip away our ozone layer, exposing the planet to deadly solar radiation. Mass extinctions have been linked to nearby gamma-ray bursts in Earth's past, events that might have wiped out large fractions of life on our planet. Fortunately, they're rare, and the stars capable of producing them are not in our immediate cosmic neighborhood. But they serve as a reminder that the universe is not just beautiful. It's dangerous, violent, capable of wiping out civilizations without warning or mercy. Now let's talk about the Sun, the star that gives us life but will eventually destroy the Earth. Our Sun is middle-aged, about 4.6 billion years old, halfway through its main sequence lifetime. It's been remarkably stable, varying in brightness by less than 1% over the course of millions of years. That stability is what allowed life to evolve on Earth. If the Sun were more variable, if it brightened and dimmed significantly, Earth's climate would be unstable, making complex life difficult or impossible. But the Sun won't last forever. In about 5 billion years, it will exhaust the hydrogen in its core. When that happens, the core will contract and heat up, while the outer layers expand. The Sun will become a red giant, swelling to a size larger than Earth's orbit. Our planet will be engulfed, vaporized in the Sun's expanding atmosphere. Even if Earth somehow survives, it will be a scorched, lifeless rock, its oceans boiled away, its atmosphere stripped, a dead world circling a dying star. After a few hundred million years as a red giant, the Sun will eject its outer layers in a planetary nebula, a beautiful shell of glowing gas expanding into space. What remains will be the core, a white dwarf about the size of Earth but with half the Sun's mass, compressed to a density where a teaspoon would weigh tons. This white dwarf will shine with leftover heat for billions of years, slowly cooling and fading until it becomes a black dwarf, a cold, dark remnant no longer emitting visible light. That's the Sun's fate. And by extension, Earth's fate. Our planet, this world that has been our home for hundreds of thousands of years, will be destroyed. Not by nuclear war or climate change or asteroid impact. By the natural death of the star that gave us life. This should put things in perspective. All of our conflicts, our wars, our politics, our struggles, all of it is temporary. The Earth itself is temporary. On cosmic timescales, everything we've ever built, everything we've ever cared about, will be erased. But that doesn't make it meaningless. If anything, it makes it more precious. We have this moment, this brief window of time where our planet is habitable, where we can exist and think and create and explore. We should make the most of it. Let me tell you about the Fermi paradox in more detail, because it's one of the most profound questions we face. Enrico Fermi, the physicist who helped build the first nuclear reactor, was having lunch with colleagues in 1950 when the conversation turned to UFOs and alien life. Fermi asked a simple question: where is everybody? If the galaxy is as old as we think, if planets are as common as we're discovering, if life arises wherever conditions allow, then where are all the aliens? Why haven't we detected them? Why haven't they visited us? Why isn't the sky filled with their radio signals and spacecraft? There are many proposed solutions to this paradox, and each one is disturbing in its own way. Maybe intelligence is incredibly rare, a cosmic fluke that happened only once in our galaxy. Maybe life is common, but complex life is rare. Maybe complex life is common, but intelligence is rare. Maybe intelligence is common, but technological civilization is rare. Maybe civilizations are common, but they're all listening and nobody's transmitting. Maybe they exist, but they're too far away, separated by distances so vast that communication is impossible. Maybe they existed in the past, but destroyed themselves before they could spread across the stars. That last one is particularly chilling. Maybe the galaxy is littered with the ruins of dead civilizations, species that developed technology, built nuclear weapons or engineered dangerous pathogens or changed their climate beyond habitability, and wiped themselves out before they could become truly spacefaring. Maybe the Great Filter, the barrier that prevents civilizations from spreading across the galaxy, is in our future, not our past. Maybe every civilization reaches a point where their technology becomes powerful enough to destroy them, and very few survive that transition. Or maybe the zoo hypothesis is correct, and advanced civilizations are out there, but they're deliberately avoiding contact, watching us from a distance like anthropologists studying an isolated tribe. Maybe there are cosmic laws against interfering with developing civilizations. Maybe they're waiting for us to reach some threshold of maturity before revealing themselves. Or maybe they're just not interested in us, considering us too primitive to bother with. Or maybe the universe is just emptier than we think. Maybe we're alone, not because we're special, but because the chain of events that leads from chemistry to biology to intelligence is so improbable that it's only happened once in the observable universe. That would make us incredibly precious, the only conscious observers in a cosmos of dead matter and energy. It would also make us incredibly lonely. We don't know which of these is correct, but we're searching. SETI continues to scan the skies for signals. New telescopes are coming online that can detect industrial pollution in the atmospheres of distant planets, signs of technology, evidence that someone else is out there. And maybe we'll find them. Or maybe they'll find us. Or maybe we'll search for centuries and find nothing but silence, forced to conclude that we truly are alone. Let me tell you about time dilation, one of the strangest consequences of relativity. Time is not absolute. It flows at different rates depending on how fast you're moving and how deep you are in a gravitational field. If you could travel at 99% of the speed of light, time for you would slow down dramatically compared to someone stationary. You could travel to a star 10 light years away and return, experiencing maybe 2 years of time, but when you got back to Earth, 20 years would have passed. Your friends and family would have aged while you stayed young. This isn't science fiction. This is real physics, confirmed by experiments with atomic clocks on airplanes and satellites. The GPS satellites orbiting Earth have to account for time dilation. Their clocks run slightly faster than clocks on the surface because they're in a weaker gravitational field. If we didn't correct for this, GPS would be off by miles within a day. And near a black hole, time dilation becomes extreme. If you fell toward the event horizon of a black hole, from your perspective, you would cross it in a finite time. But to someone watching from a safe distance, you would never quite reach it. You would appear to slow down, frozen at the edge of the event horizon, your image redshifting and fading as time itself ground to a halt. This is the strange reality of space-time. Time is not the constant backdrop we think it is. It's flexible, malleable, dependent on motion and gravity. Let me tell you about the anthropic principle and fine-tuning. The universe seems remarkably well suited for life. If the strong nuclear force were slightly weaker, atomic nuclei wouldn't hold together and complex chemistry would be impossible. If it were slightly stronger, hydrogen would fuse too easily and stars would burn out quickly. If the electromagnetic force were different, atoms wouldn't form. If dark energy were stronger, galaxies would never have formed. If it were weaker, the universe would have collapsed billions of years ago. The list goes on. Dozens of fundamental constants and initial conditions seem fine-tuned to values that allow for complexity and life. Why? One explanation is design, that some intelligence deliberately set these values. But that just pushes the question back. Who designed the designer? Another explanation is the multiverse. If there are countless universes with different physical constants, then it's not surprising that we find ourselves in one of the rare universes where life is possible. We couldn't exist in the others, so of course we observe a life-friendly universe. This is called the weak anthropic principle. Another version, the strong anthropic principle, suggests that the universe must have properties that allow life to develop at some point, though this gets into murky philosophical territory about consciousness and observation creating reality. Or maybe we're just asking the wrong question. Maybe there's a deeper theory that explains why these constants have the values they do. A theory of everything that shows these values are not arbitrary but required by some fundamental symmetry or principle. We don't have such a theory yet, but physicists are searching for it. Let me tell you about the cosmic web, the largest structures in the universe. Galaxies are not randomly distributed. They're organized into filaments and walls surrounding enormous voids, like a three-dimensional spider web of matter stretching across billions of light years. These structures form through gravity, dark matter clumping together and pulling normal matter along with it, creating the scaffolding on which galaxies formed. The filaments can be hundreds of millions of light years long, and the voids between them can be equally large, vast regions of space containing almost no galaxies at all. This structure tells us about the early universe. The pattern of the cosmic web reflects the tiny density fluctuations in the cosmic microwave background, regions that were slightly denser or less dense than average. Over billions of years, gravity amplified these fluctuations, turning them into the massive structures we see today. By studying the cosmic web, we can test our theories of how the universe evolved, whether our models of dark matter and dark energy are correct. And here's something that should make you pause. The cosmic web is growing. As the universe expands, the voids are getting larger, the filaments are stretching thinner, and galaxies are being pulled farther apart. Eventually, billions of years from now, the cosmic web will have disintegrated, galaxies isolated from each other by such vast distances that no light from one will ever reach another. The universe will become a lonelier place, each galaxy a cosmic island in an expanding ocean of darkness. Let me tell you about Titan, Saturn's largest moon, a world so strange it seems like something from an alien planet, which, of course, it is. Titan has a thick atmosphere, mostly nitrogen with some methane, denser than Earth's. It has lakes and seas, not of water but of liquid methane and ethane. It has rain, but the rain is methane. It has seasons, as Saturn orbits the Sun. It has dunes, mountains, and river valleys carved by liquid hydrocarbons. And it might have an underground ocean of liquid water, kept warm by tidal heating from Saturn's gravity. Titan is, in many ways, similar to early Earth, before oxygen filled our atmosphere. It has complex organic chemistry, the building blocks of life. It has energy sources, sunlight and cosmic rays and chemical reactions. It has liquid environments where chemistry can happen. Could life exist on Titan? Probably not as we know it. The surface temperature is minus 179 degrees Celsius, far too cold for water-based life. But maybe there's a form of life that uses liquid methane instead of water, that metabolizes in ways we can't imagine. Or maybe in the subsurface ocean, if it exists, there could be life similar to Earth's deep-sea organisms, thriving in the dark, fed by chemical energy from the moon's interior. NASA and ESA are planning a mission called Dragonfly, a nuclear-powered drone that will fly through Titan's atmosphere, landing at different sites to study the chemistry and search for signs of prebiotic processes or even life itself. It will launch in the 2030s and arrive at Titan in the 2040s. By the time you're old, we might know whether Titan harbors life, whether the chemistry we see there has crossed the line from complex molecules to biology. That's extraordinary. In your lifetime, we might discover life on another world in our own solar system. Let me tell you about cosmic rays, high-energy particles that constantly bombard Earth from space. Most are protons, the nuclei of hydrogen atoms, but some are heavier elements, and a tiny fraction are incredibly energetic, carrying more energy than anything we can create in particle accelerators. Where do they come from? The lower energy ones are from the Sun. The medium energy ones are from supernova remnants in our galaxy, particles accelerated to near light speed by the shock waves of stellar explosions. But the highest energy cosmic rays, the ultra-high energy cosmic rays, are a mystery. They have so much energy that they couldn't have come from our galaxy. They must come from extragalactic sources, possibly from the jets of supermassive black holes or from other processes we don't understand. These particles hit Earth's atmosphere and create showers of secondary particles, thousands of particles cascading down through the air. We detect them with arrays of detectors spread across huge areas, like the Pierre Auger Observatory in Argentina, which covers 3,000 square kilometers. By studying cosmic rays, we're probing the most extreme processes in the universe. Events so energetic they make supernovae look tame by comparison. And here's something to think about. Cosmic rays have been hitting Earth for its entire history. They cause mutations in DNA, possibly driving evolution in unexpected ways. They create certain isotopes that we use for radiocarbon dating. They might even have played a role in the origin of life, providing energy for chemical reactions in the early oceans. You are being hit by cosmic rays right now, particles that have traveled across the galaxy or even from other galaxies, passing through your body and potentially altering a few atoms in your cells. Most of the time, this does nothing. Occasionally, it causes a mutation, usually harmless, sometimes harmful. You are literally being touched by the most distant corners of the universe, moment by moment. Now let me tell you about quasars, among the most luminous and distant objects in the universe. A quasar is the active core of a galaxy, where a supermassive black hole is feeding on enormous amounts of matter, gas and dust, and even stars falling into the black hole at high speed. As this matter spirals inward, it heats up to millions of degrees, emitting radiation across the entire electromagnetic spectrum. A single quasar can outshine an entire galaxy containing hundreds of billions of stars. The brightest quasars are trillions of times more luminous than the Sun. Quasars are mostly found in the distant universe, meaning we're seeing them as they were billions of years ago when the universe was younger and galaxy mergers were more common. Closer to us, in the present-day universe, quasars are rare because supermassive black holes have used up most of the available fuel in their galactic cores. They're dormant, lurking at the hearts of galaxies like our Milky Way, waiting. If two galaxies merge, if new gas falls into the black hole, it could flare back to life, becoming a quasar again. This might be Earth's fate in about 4 billion years when the Milky Way collides with the Andromeda Galaxy. The merger could funnel gas into Sagittarius A star, turning our galaxy's core into a blinding quasar, sterilizing any remaining life in the galaxy with intense radiation. And here's something remarkable. Quasars are so bright that we can use them to study the universe between us and them. Light from a quasar passes through intervening gas clouds, and those clouds absorb specific wavelengths of light, creating dark lines in the quasar spectrum. By analyzing these absorption lines, we can study the composition and temperature of gas clouds billions of light years away, see how the universe's chemistry has evolved over cosmic time. We've even used quasars to study the cosmic web, detecting the vast filaments of gas connecting galaxies that are otherwise too faint to see directly. Let me tell you about the multiverse again, but from a different angle. Quantum mechanics suggests that every time a quantum decision is made, every time a particle could go left or right, the universe splits into branches where both outcomes occur. This is the many worlds interpretation of quantum mechanics, and if it's correct, there are countless parallel universes, one for every possible outcome of every quantum event that's ever happened. In one universe, you're reading this. In another, you decided not to. In another, you were never born because your parents never met. In another, humans never evolved. The number of parallel worlds is incomprehensibly vast, perhaps infinite. This sounds like science fiction, but it's a legitimate interpretation of quantum mechanics, taken seriously by many physicists. The alternative is to accept that quantum mechanics involves genuine randomness, that the universe is fundamentally probabilistic at its core, that God does play dice, as Einstein feared. Both options are unsettling. Either reality is constantly splitting into countless branches, or the universe is fundamentally random. Neither is comfortable for our human desire for a deterministic, comprehensible cosmos. Let me tell you about pulsars, rapidly spinning neutron stars that emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like a lighthouse, and if Earth happens to be in the path of one of these beams, we detect regular pulses of radio waves. Some pulsars spin hundreds of times per second, their surface moving at a significant fraction of the speed of light. They're the most accurate clocks in the universe, more stable than any atomic clock we've built. Astronomers use them to test relativity, study gravitational waves, and even search for planets around other stars by detecting the tiny timing variations caused by orbiting planets. The discovery of the first pulsar in 1967 by Jocelyn Bell Burnell was so unexpected that it was briefly considered as a possible signal from an alien civilization, jokingly called LGM-1 for Little Green Men. But we quickly realized what they were. Natural objects, the remnants of supernova explosions, spinning at incredible speeds because conservation of angular momentum means that as a star collapses, it spins faster, like a figure skater pulling in their arms. Now let me address something you might be wondering. With all these discoveries, all this knowledge, are we getting closer to a theory of everything? A single unified framework that explains all of physics, from the smallest quantum particles to the largest cosmic structures? The truth is, we're not sure. String theory, which proposes that fundamental particles are actually tiny vibrating strings in 10-dimensional space, was once considered the most promising candidate. But it has problems. It makes few testable predictions. It requires extra dimensions we can't detect. And it comes in so many variants that it's not clear which, if any, is correct. Loop quantum gravity takes a different approach, suggesting that space itself is quantized, made of discrete units at the smallest scales. But it too has struggled to make predictions we can test. Other approaches, like causal set theory or asymptotic safety, are being explored. But we're not close to a consensus. We may never have a theory of everything. Maybe physics is like an onion, with layers upon layers, each requiring its own theoretical framework, and there's no ultimate bottom layer. Or maybe we're asking the wrong questions, expecting a simplicity that doesn't exist. But that's okay. Science isn't about having all the answers. It's about asking better questions, building better theories, testing them against reality, and revising when we're wrong. The fact that we don't have a theory of everything yet doesn't mean we've failed. It means we still have work to do, mysteries to solve, discoveries waiting to be made. Let me end by bringing this back to you, to the person listening to these words. Everything I've described, every discovery, every mystery, every unanswered question, is part of your cosmic inheritance as a human being in the 21st century. You live in a time when we can peer into the very heart of black holes, detect the whispers of the Big Bang, analyze the atmospheres of planets circling other stars, and search for the signature of life beyond Earth. You live in a time when we've photographed the unseeable, heard the unhearable, and glimpsed the very edge of the observable universe. None of this was possible 100 years ago. None of it was even imaginable. And 100 years from now, our descendants will look back at our knowledge the way we look back at the medieval understanding of the cosmos, as a quaint and incomplete first step toward true understanding. They will know things we can't even conceive of. They will have answered questions we haven't thought to ask. They will have explored places we can only dream of. But this moment, right now, is uniquely yours. You get to live through these discoveries in real time. You get to witness humanity's growing understanding of its place in the cosmos. You get to be part of the first generation that can seriously ask whether we're alone in the universe and have some hope of answering that question with real data from real planets. So what do you do with this knowledge? How do you live in a universe this vast and strange and magnificent? That's up to you. But I would suggest this. Don't take it for granted. Don't become numb to the wonder of it all. Every time you look up at the night sky, remember that you're seeing across billions of light years of space and billions of years of time. Remember that you're made of atoms forged in the hearts of dying stars. Remember that you're part of a cosmic story that began 13.8 billion years ago and will continue for trillions of years to come. Be curious. Ask questions. Demand evidence. Don't accept easy answers to hard questions. The universe is complex and nuanced and often counterintuitive. It rewards those who look closely, who think carefully, who are willing to change their minds when the evidence requires it. And perhaps most importantly, remember that we're all in this together. Every human being who has ever lived, every civilization that has ever existed, all of us are passengers on this tiny planet circling an ordinary star in the suburbs of an ordinary galaxy in a universe containing hundreds of billions of galaxies. Our differences, the things we fight about, the divisions we create, they're so small compared to the cosmic perspective. We're all made of star stuff. We're all participants in the same cosmic story. We're all trying to understand the same magnificent, terrible, beautiful universe. These 30 discoveries, and the countless others I haven't had time to explore, they're not just facts and figures. They're invitations to wonder, to question, to explore. They're reminders that reality is stranger than fiction, that the universe is more magnificent than we can fully comprehend, and that we're privileged beyond measure to exist in a time when we can begin to understand it. So go forward with this knowledge. Let it change how you see the world. Let it inform your choices, your priorities, your understanding of what matters. You are part of something bigger than yourself, bigger than humanity, bigger than Earth. You are part of the universe experiencing itself, matter and energy organized in such a way that it can look back at its own history and ask why. That's extraordinary. That's miraculous. And it's yours to cherish for as long as you live. The cosmos has spoken. It has revealed its wonders and its horrors, its beauty and its violence, its order and its chaos. It has shown us ripples in space-time and storms of gamma rays, black holes and quantum entanglement, dark matter and dark energy, the very edge of space and the very beginning of time. And through it all, one truth emerges. We are capable of understanding. Against all odds, in a universe that doesn't care whether we exist, we have built instruments to see the invisible, mathematics to describe the indescribable, and theories to explain the unexplainable. That alone is worth celebrating. So celebrate it, marvel at it, be humbled by it, and carry this knowledge with you, a reminder that you live in the most extraordinary era of discovery in human history, a time when the universe itself is laying bare its secrets for those wise enough to look. This is your time. These are your discoveries. Make them count. Make them matter. And never ever stop looking up at those stars, wondering what secrets they still hold, what mysteries they're waiting to reveal to the next generation of explorers, the next chapter in humanity's cosmic journey. Because the story is far from over. We've barely begun to scratch the surface of what's out there, what's possible, what's waiting to be discovered. The universe is patient. It has been here for 13.8 billion years, and it will be here for trillions more. It will wait for us to build bigger telescopes, faster spacecraft, better theories. It will wait for us to ask the next question, make the next breakthrough, push the boundaries of human knowledge just a little bit further into the unknown. And when we do, when that next great discovery happens, when some future astronomer or physicist or explorer finds something that rewrites our understanding of reality once again, remember this moment. Remember when you first learned about gravitational waves and black holes and exoplanets and biosignatures. Remember when the universe first revealed itself to you in all its strangeness and splendor. Because that sense of wonder, that feeling of awe at the magnificence of existence, that's what makes us human. That's what drives us forward. That's what will carry us to the stars. The universe is waiting. The next discovery is out there, and you are alive to witness it. What a time to be alive. What a universe to explore. What a privilege to be part of this cosmic journey. Don't waste it. Don't ignore it. Embrace it, celebrate it, and carry it with you always. A reminder that we are part of something infinitely larger and more magnificent than ourselves. Citizens of a cosmos that never ceases to amaze and inspire those brave enough to look. But let me tell you about something that might fundamentally change how you think about time itself. We talk about the universe being 13.8 billion years old, but that's only from one reference frame. Time isn't absolute. It's relative. From the perspective of a photon, a particle of light, no time passes at all. A photon emitted from a distant quasar 13 billion years ago experiences no passage of time on its journey to Earth. From its perspective, it's created and absorbed in the same instant, even though from our perspective, it traveled for almost the entire age of the universe. This isn't metaphorical. This is the literal reality of special relativity. And it gets stranger. In a very real sense, the past still exists. Not as a memory, but as a physical reality existing in space-time. Right now, 13.8 billion years after the Big Bang, there are regions of space where observers would see the universe as it was just a few million years after the Big Bang because the light from that era is only just reaching them. The past and present coexist in the fabric of space-time, separated not by time in the absolute sense, but by spatial distance and the finite speed of light. Your past still exists somewhere in space-time. The moment you were born is still a real event, located in your past light column. The future is equally real, existing in space-time, but not yet in your causal present. This is called the block universe, and it suggests that past, present, and future all exist simultaneously in the four-dimensional structure of space-time. Does this mean free will is an illusion? That your future is already determined, already existing somewhere in space-time? Physicists and philosophers debate this endlessly. Some argue that quantum mechanics introduces genuine randomness that allows for free will. Others say that even if the future exists in space-time, we can't access it, so we still make choices even if those choices were always going to happen. It's a profound question with no clear answer, and it emerges directly from Einstein's theory of relativity, a theory that's been tested thousands of times and never been proven wrong. Now let me tell you about something called the holographic principle, an idea so radical that when it was first proposed, many physicists thought it was absurd. The principle suggests that all the information contained in a volume of space can be encoded on the boundary of that volume, like a hologram where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image. Applied to the universe, this means that everything inside a region of space, all the particles and fields and quantum states, could be described by information on the surface surrounding that region. Why would anyone think this? It comes from studying black holes. Stephen Hawking showed that black holes have entropy, a measure of disorder or information content, and Jacob Bekenstein showed that this entropy is proportional to the surface area of the event horizon, not the volume. This was shocking because normally, entropy is proportional to volume. A larger room has more entropy than a smaller room because there are more ways to arrange molecules in a larger space. But for black holes, it's the surface area that matters. This suggests that the information content of a black hole is somehow encoded on its two-dimensional surface, even though the black hole is a three-dimensional object. Physicists like Leonard Susskind and Gerard T. Hooft extended this to the entire universe, proposing that our three-dimensional reality might actually be a projection from information encoded on a two-dimensional boundary at the edge of the observable universe. This sounds like metaphysics, but it's motivated by real physics, by attempts to reconcile quantum mechanics with general relativity. And it's led to profound insights in string theory and quantum gravity. If true, it would mean that the universe is, in some sense, a hologram, a three-dimensional illusion emerging from two-dimensional information. Your body, your thoughts, your entire existence might be encoded in quantum information on a distant boundary surface. Does this make reality less real? Not at all. The hologram is the reality. We're not shadows of something more fundamental. We're the universe experiencing itself, whether that universe is fundamentally two-dimensional or three-dimensional. But it does suggest that space and dimension might not be as fundamental as we think, that they might emerge from deeper quantum structures we don't yet understand. Let me tell you about the WOW signal, one of the most tantalizing mysteries in the search for extraterrestrial intelligence. On August 15, 1977, astronomer Jerry Emin was analyzing data from the Big Ear radio telescope at Ohio State University when he saw something extraordinary. A strong narrowband radio signal, precisely at the frequency that hydrogen emits at, exactly the kind of signal you would expect from an intelligent civilization trying to communicate. The signal lasted 72 seconds, the exact amount of time it would take for Earth's rotation to move the telescope's beam across a fixed point in space. Emin was so excited that he circled the data on the printout and wrote, "Wow," in the margin. The signal has been called the WOW signal ever since. But here's the frustrating part. The signal was never detected again. Despite numerous attempts to find it, pointing telescopes at the same region of sky, using more sensitive equipment, we've heard nothing. Was it a one-time transmission from an alien civilization? Was it interference from Earth or a satellite? Was it some natural phenomenon we don't understand? We don't know. The WOW signal remains one of the great unsolved mysteries of astronomy, a tantalizing hint that maybe, just maybe, someone out there was trying to say hello, and we almost heard them. The signal came from the direction of the constellation Sagittarius, toward the dense center of the Milky Way where millions of stars cluster together. If it was from an alien civilization, they would have been advanced enough to build a powerful radio transmitter and smart enough to broadcast at the frequency hydrogen emits at, knowing that any scientifically literate species would monitor that frequency. But if they were trying to contact us, why only one signal? Why not repeat it? Unless they're broadcasting to many star systems in sequence, briefly illuminating each one before moving on, a cosmic lighthouse sweeping across the galaxy. Or maybe it wasn't for us at all. Maybe we caught a stray signal, communications between their planets or spacecraft, never intended for our ears. Or maybe it was their last transmission, a civilization that died shortly after sending it, their message drifting through space as their only legacy. These are haunting possibilities, and they remind us that the universe might be filled with voices we're not hearing, signals we're missing, civilizations that existed or exist beyond our current ability to detect. Now let me tell you about vacuum decay, a hypothetical disaster that could end the universe in an instant, and there would be absolutely nothing we could do to stop it. Remember when I mentioned that the Higgs field gives particles mass? That field exists in a state called a vacuum state, a minimum energy configuration. But quantum field theory allows for the possibility that this might not be the true minimum, that there might be a lower energy state the field could fall into. If that's the case, then our universe is in a false vacuum, a metastable state that appears stable but could suddenly transition to the true vacuum. If this transition happened anywhere in the universe, it would create a bubble of true vacuum expanding at the speed of light. Inside the bubble, the laws of physics would be different. Particles would have different masses. Chemistry would be impossible. Atoms as we know them wouldn't exist. The bubble would grow relentlessly, converting everything it touched into this new configuration. Stars, planets, galaxies, everything would be destroyed and replaced with a fundamentally different kind of physics. And we would never see it coming. The bubble wall would be traveling at the speed of light, so there would be no warning, no signal that could outrun it. One moment, you're reading this. The next, you and everything around you are converted into exotic particles governed by unfamiliar laws. It would be the ultimate catastrophe, the end not just of life but of the physical laws that allow complex structures to exist. Is this going to happen? We don't know. Calculations suggest that the Higgs field might be metastable, hovering near the boundary between stability and instability. It could be stable for longer than the current age of the universe, or it could decay tomorrow. We have no way of knowing. But here's a strange thought. If vacuum decay is possible, why hasn't it happened yet in the 13.8 billion years since the Big Bang? Maybe we're just lucky. Maybe the probability is so low that even over cosmic timescales, it hasn't happened in our observable universe. Or maybe it has happened elsewhere, in distant regions of space beyond our cosmic horizon, and we just haven't been touched by it yet. Or maybe some mechanism we don't understand makes the vacuum genuinely stable. This is the kind of existential uncertainty we live with. The universe could end at any moment, and there's nothing we could do about it. But this is true of many things. A nearby star could go supernova and bathe Earth in deadly gamma rays. A massive asteroid could strike without warning. The sun could emit a superflare that strips our atmosphere. We live in a universe that's indifferent to our survival, a cosmos governed by laws that don't care whether we exist or not. And yet we persist. We build civilizations, create art, explore the stars, and ponder our place in the universe. Our defiance in the face of cosmic indifference is perhaps the most human thing about us. Let me tell you about the Tunguska event, a reminder that Earth exists in a shooting gallery and we're hit more often than we realize. On June 30th, 1908, something exploded over a remote region of Siberia with the force of 15 megatons of TNT, 1,000 times more powerful than the Hiroshima bomb. The explosion flattened 80 million trees over an area of 2,000 square kilometers. If it had occurred over a populated city, the death toll would have been catastrophic. But because it happened in an isolated forest, there were few witnesses and no confirmed deaths. What was it? The leading theory is that a small asteroid or comet, perhaps 40 to 60 meters across, entered Earth's atmosphere and exploded at an altitude of about 6 kilometers due to air friction and pressure. The object was completely destroyed in the explosion, which is why no impact crater was found. But it's a sobering reminder that Earth is constantly being bombarded by space debris, most of it small enough to burn up harmlessly in the atmosphere, but occasionally something larger gets through. We've since detected thousands of near-Earth asteroids, objects whose orbits bring them close to our planet. A few of these are classified as potentially hazardous, meaning they're large enough to cause regional or global devastation, and their orbits could potentially intersect Earth's. We're tracking them, watching for any that might pose a threat. And we're developing technologies to deflect them, spacecraft that could nudge an asteroid off course years before it would hit us. In September 2022, NASA's DART mission successfully crashed into an asteroid and changed its orbit, proving that we can defend ourselves if we have enough warning. But here's the terrifying part. We've probably only found about 90% of the largest, most dangerous asteroids. There are thousands of smaller ones we haven't detected yet, objects large enough to destroy a city but small enough to evade our surveys. One of these could hit us with little or no warning. And there's nothing we could do about a comet from the outer solar system if it suddenly fell sunward on a collision course with Earth. By the time we detected it, we would have only months or weeks to react, nowhere near enough time to launch a deflection mission with current technology. This is why space agencies around the world are working on planetary defense systems, networks of telescopes scanning the sky for threats, spacecraft ready to launch on short notice, international protocols for what to do if we detect an incoming impactor. We've gone from being helpless against cosmic impacts to having at least a fighting chance, if we have enough warning. It's one of the few existential threats we're actually preparing for, and it gives me hope that when we face the challenges ahead, whether from climate change or technological risks or future cosmic threats, we're capable of working together to protect our species. Now let me tell you about something deeply unsettling that challenges our understanding of logic itself. Quantum mechanics allows for phenomena that seem to violate basic principles of reasoning. Take quantum superposition. A particle can exist in multiple states simultaneously until you measure it, at which point it chooses one state. This isn't ignorance about which state it was in. The particle genuinely was in multiple states at once, described by a mathematical combination called a superposition. Schrödinger's famous thought experiment with the cat in the box, simultaneously alive and dead until you open the box and observe it, was meant to show how absurd this is when applied to everyday objects. But at the quantum level, it's literally true. Or consider the double-slit experiment. Fire electrons one at a time at a barrier with two slits. Each electron goes through the barrier and hits a screen on the other side. Over time, the electrons build up an interference pattern, alternating bands of light and dark, exactly the pattern you'd expect if each electron was a wave that went through both slits and interfered with itself. But if you put detectors at the slits to see which one each electron goes through, the interference pattern disappears. The electrons behave like particles going through one slit or the other. The act of measurement changes the outcome. It's as if the universe doesn't have definite properties until you look, as if reality is fuzzy and indeterminate until consciousness forces it to choose. This has led some physicists to suggest that consciousness plays a fundamental role in quantum mechanics, that the universe requires observers to collapse quantum states and make reality definite. This seems absurd. It suggests the universe before the evolution of conscious life was somehow unreal or indeterminate. But delayed choice quantum eraser experiments have shown effects even stranger than that. Cases where measurements in the present seem to affect events in the past, or where information about which path a particle took can be erased after the particle has already made its decision, retroactively changing what happened. What does this mean? We don't know. Interpretations of quantum mechanics range from many worlds, where every quantum possibility spawns a new universe, to pilot wave theory, where particles are guided by deterministic waves, to quantum Bayesianism, where quantum states represent our knowledge rather than reality itself. Each interpretation preserves the mathematics and predictions of quantum mechanics, but offers a radically different view of what's actually happening. And we have no way to distinguish between them empirically because they all make the same predictions. This means that at the deepest level, we don't understand reality. We have incredibly accurate mathematical models. We can predict the outcomes of experiments to extraordinary precision. But we don't know what it means. We don't know what the universe is doing when particles are in superposition, or what measurement actually does, or whether reality exists independently of observation. These are not minor philosophical quibbles. They're fundamental questions about the nature of existence, and after a century of quantum mechanics, we're no closer to consensus. Let me tell you about Betelgeuse, a star you can see with your naked eye in the constellation Orion. It's a red supergiant, about 700 light-years away, and it's one of the largest stars known, with a radius about 700 times that of the Sun. If you replace the Sun with Betelgeuse, the star's surface would extend past the orbit of Mars. And it's dying. Betelgeuse has exhausted much of its fuel and is in the late stages of stellar evolution. At any time, it could explode as a supernova. It might have already exploded, and we won't know for 700 years because that's how long light takes to reach us from there. When it does explode, it will be spectacular. For a few weeks or months, Betelgeuse will be visible during the daytime, as bright as the moon. It will cast shadows at night. It will be the brightest supernova in human history, brighter than any that's been recorded, and we'll be able to study it in unprecedented detail with all our modern telescopes and detectors, learning about stellar death and element formation in ways we've never been able to before. Will it harm Earth? No. 700 light-years is far enough that the radiation from the supernova will be diluted to safe levels by the time it reaches us. We'll get to watch one of the universe's most violent events in safety, a cosmic fireworks show courtesy of a dying giant star. And astronomers are eagerly waiting for it to happen, hoping it occurs during their lifetimes so they can observe and study it. But here's the thing. Betelgeuse has been shrinking and dimming in recent years, and in late 2019, it suddenly dimmed significantly, losing more than half its brightness. Was this a sign that the supernova was imminent? Astronomers around the world turned their telescopes toward it, collecting data frantically. But the star eventually brightened again. It turns out the dimming was caused by a massive dust cloud ejected from the star's surface, temporarily blocking its light. Betelgeuse wasn't about to explode after all. But the event reminded us how uncertain stellar physics can be. We have models that predict when stars should go supernova, but those models have large error bars. Betelgeuse could explode tomorrow or in 100,000 years. We don't know. And that uncertainty is both frustrating and exciting. When it does happen, whenever that is, it will be one of the great astronomical events in human history. Let me tell you about the Kuiper Belt and the Oort cloud, regions at the edge of our solar system that we're only beginning to explore. The Kuiper Belt is a region beyond Neptune's orbit, from about 30 to 50 astronomical units from the Sun, filled with icy bodies left over from the solar system's formation. Pluto is the most famous Kuiper Belt object, but there are thousands of others, ranging from small rocks to dwarf planets larger than Pluto. This is where short-period comets come from, icy bodies whose orbits are disturbed by Neptune's gravity, sending them sunward where they melt and develop tails. Beyond the Kuiper Belt, much farther out, perhaps 50,000 astronomical units from the Sun, is the Oort cloud, a spherical shell of icy bodies surrounding the entire solar system. We've never directly observed the Oort cloud because its objects are too distant and too faint, but we know it must exist because that's where long-period comets come from, comets that take thousands of years to orbit the Sun. These comets have orbits that bring them in from all directions, suggesting they come from a spherical distribution of objects rather than a flat disk like the Kuiper belt. The Oort cloud marks the edge of the Sun's gravitational influence, the boundary between our solar system and interstellar space. Objects in the Oort cloud are so distant that they're barely bound to the Sun, and passing stars can perturb their orbits, sending some plummeting toward the inner solar system as comets. The Oort cloud is a relic of the solar system's formation. Icy planetesimals ejected outward by the gravity of the giant planets billions of years ago. And here's something to consider. If our solar system has an Oort cloud, then every other star system probably does too. Interstellar space isn't empty. It's filled with clouds of icy bodies surrounding every star, and occasionally these clouds overlap. Objects from other stars' Oort clouds might occasionally wander into our solar system. Oumuamua might have come from another star's Oort cloud, an iceberg ejected billions of years ago and wandering through the galaxy until it happened to pass through our cosmic neighborhood. Now let me tell you about redshift and how it reveals the universe's expansion. When an object is moving away from you, the light it emits is stretched to longer wavelengths, shifted toward the red end of the spectrum. This is the Doppler effect for light, analogous to how an ambulance siren sounds lower-pitched as it drives away from you. Edwin Hubble discovered in the 1920s that distant galaxies are redshifted, and the farther away they are, the more they're redshifted. This means the universe is expanding, with galaxies moving away from each other as space itself expands. But here's the subtle part. The galaxies aren't moving through space. Space itself is expanding, carrying the galaxies along with it. It's like dots painted on a balloon. As you inflate the balloon, the dots move apart, not because they're sliding across the surface, but because the surface itself is stretching. From any dot's perspective, all the other dots appear to be moving away, and the farther dots move away faster. There's no center to this expansion. Every point in space sees every other point receding from it. This expansion has profound consequences. Light from distant galaxies is redshifted so much that it moves out of the visible spectrum entirely, shifting into the infrared or even radio wavelengths. The most distant galaxies we can see with Webb are so redshifted that their ultraviolet light has been stretched into the infrared. And there's a cosmic horizon, a distance beyond which light has not had time to reach us since the Big Bang. Currently, that horizon is about 46 billion light-years away, not 13.8 billion. Because space has been expanding while the light traveled. Beyond that horizon, there are regions of space we can never see, will never see, because the light from them will never reach us. And as the universe continues to expand, driven by dark energy, this horizon will shrink. Galaxies currently visible will eventually recede beyond our cosmic horizon, disappearing from view forever. In the far future, trillions of years from now, civilizations in our galaxy will look out at the sky and see nothing but darkness, no other galaxies visible, all of them having receded beyond the horizon. They won't know about the Big Bang or the cosmic microwave background or the expansion of the universe because all the evidence will have disappeared. They'll think they live in a static universe containing only their own galaxy. They'll be cosmologically isolated, cut off from the truth about their cosmos. We're lucky to exist in an era where we can still see the universe's history written in the light from distant galaxies. Let me tell you about nuclear fusion, the process that powers the stars and might someday power human civilization. At the core of the Sun, under pressures millions of times greater than Earth's atmosphere and temperatures of 15 million degrees Celsius, hydrogen nuclei fuse together to form helium, releasing energy in the process. This is the source of the Sun's light and heat, the energy that makes life on Earth possible. Every second, the Sun converts about 600 million tons of hydrogen into helium, and in the process, loses about 4 million tons of mass, which is converted into pure energy according to Einstein's equation E=mc². Humans have been trying to replicate this process on Earth for decades. If we could harness fusion, we'd have a nearly limitless source of clean energy. The fuel for fusion, hydrogen isotopes like deuterium and tritium, can be extracted from seawater. The reaction produces helium and neutrons, with no carbon emissions and minimal radioactive waste compared to fission reactors. It would solve our energy crisis. But fusion is hard, really hard. You need to heat plasma to tens of millions of degrees and confine it long enough for fusion to occur, all while extracting more energy than you put in. Magnetic confinement reactors like tokamaks use powerful magnetic fields to contain the plasma. Inertial confinement reactors use lasers to compress pellets of fuel until they ignite. Despite decades of effort, we've only recently achieved ignition, where a fusion reaction produces more energy than was delivered to the fuel, and we're still far from a reactor that produces more energy than the entire facility consumes. But we're getting closer. In December 2022, the National Ignition Facility in California achieved fusion ignition for the first time, proving that it's possible. Private companies are developing new reactor designs, and several countries are building experimental reactors. Within your lifetime, we might see the first commercial fusion power plants, providing clean, abundant energy for human civilization. It would be one of the great achievements in human history, harnessing the power source of the stars themselves. And here's something to consider. If we achieve fusion, if we develop the technology to build reactors that power cities and spacecraft, we'll have taken a crucial step toward becoming a truly spacefaring civilization. Fusion could power interplanetary ships, allowing us to explore the outer solar system more quickly and efficiently. It could power colonies on Mars or the moons of Jupiter and Saturn. It could be the key to leaving Earth permanently, spreading human civilization across multiple worlds and ensuring our species' long-term survival. Let me tell you about one more discovery that should make you pause and think. In 2003, a group of astronomers discovered what they call the Great Wall, a massive structure of galaxies stretching across 500 million light-years of space. It's one of the largest structures ever detected, a filament of the cosmic web containing thousands of galaxies. But it's not the only one. We found other massive structures. The Sloan Great Wall, the Huge Large Quasar Group, the Hercules Corona Borealis Great Wall, which might be 10 billion light-years across, challenging theoretical limits on how large structures in the universe can be. These structures formed from the initial density fluctuations in the early universe, regions that were slightly denser attracting more matter through gravity over billions of years. But their size pushes against what's called the cosmological principle, the assumption that the universe is homogeneous and isotropic at large scales, that there should be no structures larger than a certain size because there hasn't been enough time for gravity to assemble them. Yet here they are, challenging our assumptions about how the universe should look. Do they mean our cosmological models are wrong? Probably not fundamentally, but they might mean we need to refine them to account for structures larger than we expected. Or they might just be statistical flukes, rare configurations that happen to exist in our observable universe but wouldn't be typical if we could see a larger volume of space. We don't know. But they're reminders that the universe is big, far bigger than we can comprehend, and it contains structures and phenomena we're only beginning to catalog and understand. Let me bring this full circle back to you, to the person experiencing these words. You've just taken a journey through 13.8 billion years of cosmic history, from the Big Bang to the present, from the smallest quantum fluctuations to the largest structures in space, from the beginning of time to its potential end. You've learned about black holes and neutron stars, dark matter and dark energy, gravitational waves and quantum entanglement, exoplanets and biosignatures, the death of stars and the birth of galaxies. But more than that, you've glimpsed the process of discovery itself, how humanity went from ignorance to knowledge, from superstition to science, from thinking Earth was the center of everything to realizing we're a tiny planet orbiting an ordinary star in an ordinary galaxy among billions of galaxies. You've seen how each discovery raised new questions, how each answer revealed deeper mysteries, how the more we learn, the more we realize how much we don't know. This is the human condition in the cosmic age. We're caught between knowledge and ignorance, between understanding and mystery. We know enough to ask profound questions, but not enough to answer all of them. We can detect gravitational waves and photograph black holes, but we don't know what dark matter is or why the universe exists. We can analyze the atmospheres of planets 40 light-years away, but we can't say for certain whether we're alone in the universe. We can trace cosmic history back to a fraction of a second after the Big Bang, but we don't know what came before or why the laws of physics are the way they are. And that's okay. That's beautiful, actually, because it means there's still work to do, still mysteries to solve, still discoveries waiting to be made. The universe hasn't revealed all its secrets. It's given us enough to tantalize us, to show us the shape of the mystery, but not enough to satisfy our curiosity completely. And that's perfect, because curiosity is what makes us human. The desire to know, to understand, to push back the boundaries of ignorance and see what's hiding in the darkness, that's our defining characteristic as a species. So here's my final challenge to you. Take what you've learned here and let it change you. Don't just know these facts intellectually. Feel them emotionally. Let the scale of the universe humble you. Let the age of the cosmos put your problems in perspective. Let the possibility of other life in the universe excite you. Let the mysteries we haven't solved yet intrigue you. Let the beauty of it all inspire you. And then take action. Support space exploration and scientific research. Vote for policies that fund telescopes and spacecraft and experiments. Encourage young people to pursue careers in science and engineering. Share these discoveries with others. Spread the wonder and the knowledge. Combat ignorance and pseudoscience with facts and evidence and critical thinking. Be part of the generation that pushes human knowledge forward, that answers old questions and asks new ones, that reaches for the stars not just metaphorically but literally. Because this is your inheritance and your responsibility. You've been given the privilege of living in a time of unprecedented discovery, when the universe is revealing itself at an extraordinary rate. But privilege comes with obligation. You have a duty to preserve and extend this knowledge, to ensure that future generations know even more than we do, that they have even better tools and theories and understanding than we've achieved. The cosmos is waiting for you. It has been waiting for 13.8 billion years, preparing the stage, setting the conditions, allowing matter to organize itself into stars and planets, and eventually into conscious beings capable of looking back and asking why. You are the universe's way of knowing itself. Matter arranged in such improbable complexity that it can ponder its own existence. Don't waste that. Don't take it for granted. Use it. Question everything. Demand evidence. Think critically. And above all, never stop wondering. Never stop asking. Never stop looking up at those stars and marveling at the magnificent, terrifying, beautiful cosmos that we're privileged to call home. The 30 discoveries I've shared with you are just the beginning. There are thousands more I haven't mentioned, thousands more being made right now, thousands more waiting in the future. The detection of phosphine on Venus and its controversy. The discovery of fast radio bursts and their mysterious origins. The mapping of dark matter in galaxy clusters through gravitational lensing. The detection of neutrinos from the Sun and from supernovae, ghostly particles that pass through the Earth as if it weren't there. The discovery of cosmic voids, vast empty regions of space containing almost no galaxies. The observation of galaxy mergers in action, watching cosmic collisions unfold over millions of years. The measurement of the cosmic microwave background's polarization, revealing the universe's earliest moments. Each of these could be its own documentary, its own story of human curiosity and perseverance and brilliance. But we're out of time. The universe has spoken through gravitational waves and gamma rays, through radio signals and infrared light, through the mathematics of physics and the observations of dedicated scientists around the world. It has told us its story, or at least the parts of the story we're capable of understanding with our current technology and theories. And what a story it is. A universe born in fire, expanding and cooling, forming stars and galaxies, heavy elements and planets, and eventually life and consciousness and wonder. You are part of that story. Not a passive observer, but an active participant. Your atoms were forged in stars. Your existence required 13.8 billion years of cosmic evolution. Your ability to understand these discoveries makes you one of the universe's most complex and improbable structures. Don't waste it. Don't squander this cosmic inheritance. Live up to it. Be worthy of it. Look up. Wonder. Explore. And never, ever forget that you are made of star stuff, that you are the cosmos experiencing itself, and that's the most extraordinary thing in the entire universe. Before I leave you, let me share one last thought that ties everything together. Think about all the discoveries we've discussed. The gravitational waves from colliding black holes, detected by instruments so sensitive they can measure changes smaller than an atom. The potential biosignatures on K2-18b, chemicals in the atmosphere of a planet 124 light-years away. The James Webb Space Telescope, showing us galaxies from when the universe was just a few 100 million years old. The discovery of thousands of exoplanets, each one a world with its own story, its own history, its own potential for harboring life. The mapping of dark matter through its gravitational effects, even though we can't see it or touch it. The detection of interstellar visitors like Oumuamua, messengers from other star systems passing through our cosmic neighborhood. The observation of supernovae and gamma-ray bursts, the most violent events in the cosmos. The exploration of our own solar system, finding oceans beneath the ice of Europa and Enceladus, methane lakes on Titan, ancient riverbeds on Mars. All of this, every single discovery, happened because humans refused to accept ignorance. We looked up at the night sky and demanded answers. We built telescopes and spacecraft and detectors. We developed mathematics and physics and chemistry. We asked questions that seemed impossible to answer and then figured out how to answer them anyway. We detected the undetectable, photographed the unphotographable, understood the incomprehensible. That's the real miracle here. Not that the universe exists or that it's so vast and ancient and complex. The miracle is that we, a species that evolved on a small planet orbiting an average star in an ordinary galaxy, have managed to figure out so much about the cosmos that created us. Think about the challenges we've overcome. For most of human history, we couldn't see beyond our own atmosphere. We were trapped on Earth, looking up at points of light we didn't understand. Then we invented telescopes. Then we sent spacecraft to other planets. Then we built detectors sensitive enough to feel the whisper of gravitational waves from events a billion light-years away. Then we developed the technology to analyze starlight and determine the chemical composition of distant planets. Each step seemed impossible until we made it possible. Each barrier seemed insurmountable until we surmounted it. And we're not done. Not even close. Right now, engineers are designing the next generation of telescopes that will be even more powerful than Webb. The extremely large telescope in Chile, with a mirror 40 meters across, will be able to directly image Earth-like planets around nearby stars. The Nancy Grace Roman Space Telescope will map dark matter across vast swaths of the sky. The proposed LISA mission will detect gravitational waves from space, finding signals LIGO can't reach. Future missions to Europa and Enceladus will search for life in their subsurface oceans. Spacecraft are being planned that could reach nearby stars within a human lifetime, sending back images of other planetary systems. And that's just what we're planning with current technology. Imagine what we'll be capable of in 50 years, in 100 years, in 1,000 years if we survive that long. We might build telescopes on the far side of the moon, free from Earth's interference. We might establish colonies on Mars and the moons of Jupiter and Saturn. We might send generation ships to other star systems, carrying human civilization to the stars. We might discover the nature of dark matter and dark energy. We might unify quantum mechanics and general relativity into a theory of quantum gravity. We might make contact with an alien civilization, exchanging messages across light years of space. We might even, eventually, understand why the universe exists at all. Or we might destroy ourselves first. That's the sobering reality we have to face. We have the technology now to wipe ourselves out through nuclear war, engineered pandemics, runaway artificial intelligence, or environmental collapse. We're in a precarious position, having developed the power to fundamentally alter our planet and our future before we've developed the wisdom to use that power responsibly. The next century will determine whether humanity becomes a lasting, multi-planetary civilization or just another failed experiment in cosmic evolution. That's why these discoveries matter. They're not just interesting facts to entertain us. They're reminders of our potential, of what we're capable of when we work together toward common goals. They're evidence that we can solve seemingly impossible problems, that we can overcome our limitations, that we can reach beyond our immediate concerns and grasp for something greater. If we can detect gravitational waves and photograph black holes and find potential signs of life on distant planets, then surely we can figure out how to work together to solve climate change, eliminate nuclear weapons, prevent pandemics, and ensure our species' survival. The universe has given us everything we need. It has given us a planet with liquid water and a protective magnetic field and an atmosphere that shields us from radiation. It has given us a star that's stable enough to allow life to evolve over billions of years. It has given us a galaxy rich in heavy elements, the products of countless supernovae, providing the materials needed for complex chemistry and technology. It has even given us the laws of physics, mathematical and comprehensible, allowing us to understand and predict how reality works. We've been handed an extraordinary gift. The question is whether we're wise enough to preserve it. So when you look up at the stars tonight, when you think about everything I've told you, remember this. You're not just a witness to the universe. You're a participant in its unfolding story. Your choices matter. Your actions have consequences that ripple out into the future. What you do with this knowledge, how you live your life, what values you uphold, the compassion you show to others, the curiosity you nurture in yourself and those around you, all of it contributes to whether humanity thrives or perishes, whether we reach the stars or destroy ourselves before we get the chance. The cosmos has been preparing for this moment for 13.8 billion years. It has created stars and planets, elements and molecules, energy and matter, space and time, all leading to this. Conscious beings capable of understanding their own origins, capable of asking profound questions about existence, capable of reaching beyond their planet to explore the universe that created them. You are the culmination of that cosmic evolution. You are what the universe has been building toward. Don't waste that inheritance. Don't squander that potential. Live up to it. Be worthy of the billions of years of cosmic history that made your existence possible. And when you feel small, when the vastness of the universe seems overwhelming, remember that you're not small at all. You're a complex, conscious being capable of understanding mathematics and physics, capable of appreciating beauty and creating art, capable of love and compassion and wonder. You're made of atoms that were forged in the hearts of stars, scattered across space in supernova explosions, and eventually gathered together on a planet where conditions were just right for life to emerge. Your very existence is a statistical miracle, an improbable arrangement of matter and energy that somehow became self-aware and started asking questions about the universe it inhabits. That's not small. That's extraordinary. You're part of the most complex and improbable phenomenon we know of, conscious life. In a universe of dead matter and empty space, you are a pocket of order and awareness, a temporary reversal of entropy, a brief but brilliant flash of consciousness in the cosmic dark. Make it count. Make it mean something. Use your time in this universe to learn, to grow, to create, to explore, to connect with others, to leave the world a little better than you found it. The 30 discoveries I've shared are your roadmap to understanding the cosmos. They're milestones in humanity's journey from ignorance to knowledge. But they're not the destination. They are waypoints along an infinite path of discovery that will continue long after you're gone. Your role is to carry the torch forward, to add your own small contribution to human knowledge and understanding, to ensure that the next generation inherits a world where curiosity is valued, where science is respected, where truth is sought and treasured. So go forth with this knowledge. Let it transform you. Let it humble you and inspire you and fill you with wonder. Let it remind you that you're part of something infinitely larger than yourself, a cosmic story that began with a Big Bang and will continue for trillions of years into the future. You're a brief chapter in that story, a momentary arrangement of atoms that will eventually return to the cosmos. But while you're here, while you have consciousness and awareness and the ability to understand, make the most of it. Look up at those stars. Ask those questions. Seek those answers. And never forget that you are the universe experiencing itself, and there is nothing more precious or extraordinary in all of existence than that.